my science fair presentation about if the color of food will affect how we like it. My question was, will the color of food change how we like it? My research and information said that the color of food would change how we like it depending if we like the color or not and our age. My hypothesis. The color of food or drink will not change how we like that food or drink. Materials. I used water, milk, egg, M&Ms, and top ramen. Procedures. I first had to dye all the food. I had one of the twins pick which one they wanted, colored or normal, see which one they liked more, jot it down, and then repeat with the other twin. My notes. They were excited to try the different foods. They really wanted to see what each other were choosing. Nash chose the regular ramen and said the regular ramen tasted better. Nash picked regular egg but said the green egg tasted better. Nash picked the blue milk but said the blue milk tasted better. Nash picked red water and said red water tasted better than the normal water. Nash picked colored M&Ms and liked the colored ones more. Parker picked green ramen and said they tasted the same. Parker chose green eggs and said regular tasted better. Parker picked blue milk and said blue milk tasted better. Parker chose regular water but said red water tasted better. Parker picked brown M&Ms and said it tasted better than colored M&Ms. They had sort of different answers, but they said it was fun to do at the end. Conclusion. The color of drinks and foods does change how we like it. And then these were the photos of Nash. And these were the photos of Parker. Thank you.
What hand sanitizers are effective? By Zoe Mosher. What hand sanitizers are most effective? What hand sanitizers are not effective? Materials. I'm using a pen, tissue paper, doTERRA On God hand sanitizer, SafeTech Fresh hand sanitizer, Victoria's Secret Honey Pomelos hand sanitizer, and Bath & Body Works Cactus Bloom hand sanitizer. This is my copied research. Now pour some drops of hand sanitizer inside this circle. If the ink starts to fade away and spills, it means your hand sanitizer is fake. But if the circle remains as it is, and the paper also dries quickly, this indicates your hand sanitizer is of good quality and effective. If I test 4 hand sanitizers, then I'll find out which hand sanitizer is most effective. Here are like my steps. So first, I got out the materials from my experiment. Second, I put a drop of hand sanitizer in each tissue. Then I wait to see if the hand sanitizer fades or not. If the hand sanitizer fades, it's fake. And if the hand sanitizer doesn't fade, it's good hand sanitizer. Has good quality. This is the picture of my hand sanitizers. And actually here are the videos.
So here are the results. This is the first most effective out of all of them, the SafeTech Fresh hand sanitizer. This is the second most effective out of all of them. This is the Bath & Body Works Cactus Bloom. And this is the third most effective out of all of them, the doTERRA On Guard. But this one it showed was not effective because it faded away and spilled. But the Cactus Bloom and SafeTech ones are effective. And this one is the fourth most effective. It's actually not effective because it spilled. This is the Victoria's Secret hand sanitizer, Honey Pomelo. It spilled, so that was not effective.
Now here's my other video. And so those were the videos. And here are my notes. Expected the SafeTech hand sanitizer not to be effective and the doTERRA hand sanitizer to be effective, but it turned out differently. At first, I didn't know what to expect. Then some unexpected hand sanitizer started fading, and everything went unexpected. These are the results. The number one most effective is SafeTech Fresh hand sanitizer. The number two, which is effective, which is the Bath & Body Works Cactus Bloom hand sanitizer. And the third, not like really effective, but still is effective, is the doTERRA On Guard hand sanitizer. And number four, the least effective, is the Victoria's Secret Honey Pomelo hand sanitizer.
My science fair project was about caffeine. My question was, how does different levels of caffeine affect your heart rate? My research and information showed that the caffeine the effects of caffeine can be felt around 15 minutes later, and then it also showed how it affects the adrenaline the adrenaline in your blood. My hypothesis was consuming more than 70 milligrams of caffeine will slightly raise your heart rate within 15 minutes of consumption. My materials were a stopwatch for monitoring heart rate over 1 minute. My drinks were coffee, energy drink, iced tea, Diet Coke, and then espresso, and then I forgot to add one more. I think it was hot tea. Yeah, hot tea. Okay, so my procedures were, I measured each person's regular heart rate. Each person consumed a caffeinated beverage within a specific amount of caffeine. I measured their heart rate 15 minutes later, and again 1 hour later. I did this each day with a different drink with a different amount of caffeine until I tested 5 drinks. Okay, so these were just my drinks that I had and everything. These are my notes. So before, I noticed that the smallest person had the highest resting heart rate. I had the same resting heart rate as an adult. During the project, I disliked the taste of most drinks. I observed my 9-year-old brother feeling very sick and jittery after he drank the Red Bull, which had the most caffeine. It had the longest effect on anyone, and he did not feel right for about 5 hours. I noticed that the first night I drank caffeine, I had a very hard time falling asleep, even though I drank it very early in the morning. After all the drinks and charting all of my data, I noticed that the adult who had the highest body weight had the smallest change in heart rate. Only the energy drink made it rise even a little bit. The smallest person had the biggest change in heart rate, with its rising a lot after espresso and Red Bull, which have a higher amount of caffeine. These are all the things that just happened. These are like the heart rate and everything. Okay, so my conclusion, my hypothesis was kind of correct that a beverage with more than 70 milligrams of caffeine did change a person's heart rate, but it became noticeable that a person's body weight also mattered. The lower the person's body weight, the more the caffeine seemed to affect their heart rate. The higher their body weight was, the less changes occurred. So that was what happened during my experience. So for this thing, and yeah.
So I'm Abigail Grant, and this is my presentation, my Science for Purchase presentation. So these are my pennies before I put them in, and as you can see, I marked them 1, 2, 3, and 4, and I put them in for 25 minutes each. This is when I put them in. I just marked them 1, 2, 3, and 4 again. And V stands for vinegar, L stands for lime juice, and AV stands for apple cider vinegar. Lastly, BS stands for baking soda. I was testing to see if it would do anything if I put a penny in baking soda and vinegar. In 4, I did lime juice and in baking soda, and in 3, I did baking soda and vinegar. In 2, I did lime juice and apple cider vinegar. In 1, I did lime juice and vinegar. And this is them after I put them in for 25 minutes. And when you take a look at them, you can see that they're marked again. They're marked exactly in their order. The first was number 1, second was number 2, third was number 3, and fourth was number 4. It's kind of weird how their order went, but that's okay. So the first one was regular vinegar and lime juice. The second one was apple cider vinegar and lime juice. Third place was lime juice and baking soda. And for fourth place, we have baking soda and vinegar. It didn't really do anything that much, but that's okay. And also, my prediction came true. I didn't think that baking soda and vinegar would do that much to the penny, but I did think that vinegar and lime juice would do something more to number 1, and it came true. Number 1 was first place, and number 4 was fourth. I ordered them as they were done, like I'd ordered them numbers by what I thought their placement was going to be, and that's why it came true like that. Actually, I'm not so sure why it came true like that, but okay. And that's all. And thank you for watching.
Welcome, I am Alex, and I'm Alex E, and I am presenting my science project. So what is your fruits timeline? It's just basically how long does it take till you can't eat your fruit, how fast it molds, how slow it molds, if it changes color or not, if it shrinks, if it does weird stuff. That's all science fair is about, okay? Question, I'm sorry, it's really short. Which fruit molds fastest and slowest? Natural foods mold faster. The moisture and nutrients in fruit attract mold. Yep. Hypothesis. According to the website, wellandgood.com, bananas have the least moisture and watermelons and strawberries have the most. So I predict that the strawberries, for some reason, not the watermelons, will mold fastest and bananas will mold slowest. Materials, a lot of fruit, yep. A place to put it, and that was my garage and my dining table. There's 2. And then camera for check-ins, I only did before and after, so I was gonna do check-ins, but then, I don't know what happened. Procedure, get fruit, yep. 2, put it in place. 3, experiment off. And 4, type conclusion. I predict the watermelon and strawberries won't, okay, so this is just the notes, this is just what happens. I predict the watermelon and strawberries will mold fastest and the green banana will mold slowest. Keep in mind that the fruit will be in the garage, so that might change the outcome. Hopefully too many bugs don't come. I didn't see any bugs, so it's fine. Fruit included apples. I said apple. Apple, grapes, green bananas, lemon, pineapple, strawberries, and watermelon. So during bananas first to show mold, watermelons look awful, pineapples closing in. Watermelons have mold and is mushy and gross. Bananas brown, no mold. Grapes, apple look okay. Lemons look fine. Strawberries are looking strange. And it went from May 5th to May 12th. It was only 1 week. It's fine. So this is the before picture. Sorry, it's small. And after, you can see the watermelon isn't looking great. Pineapple, like I said, closing in. I don't really know how to say this. It's like, you can see mold in there, right? Yeah. It's like the sides are like coming together to make it like a taco shell. Bananas are all brown. Lemons are hot, dude. They're like, okay. Conclusion. Alright, in conclusion, the watermelon's moisture and sweetness made it mold fastest. The watermelon molds in approximately 4 days. On the other hand, the lemon didn't move a slice. I believe that the acid in the lemon that makes it sour helps preserve it from deteriorating. Overall, the lemon looks the most fresh out of the group. The apple looks the second best, and third place goes to the banana, which turned brown and slightly shrinked. My hypothesis was incorrect because I thought the strawberry will mold fastest and the banana will mold slowest. So what we've learned is that the least moisture and acidity, which if you don't know what that is, it's just sourness, equals rotted fruit. You can see the banana. See the pineapple? It's moldy in the middle. That is my science project. I hope you liked it, and yeah, I'm out.
My science fair project was which leather cleaning product cleans the bridle the best. What leather cleaning product will clean the bridle the best? I wonder if the soap and water will clean the bridle just the same as the leather cleaners. Research and information. According to Kentucky Mountain Saddle Horse News, it says a saddle or bridle does the best when you keep it clean and well oiled. Never clean with harsh detergents or hot water. Natural soaps such as Murphy's Oil Soap, liquid glycerin soaps, or glycerin bars with lukewarm water are the best. Hypothesis. If I get the best cleaner, what one will clean it the best? Materials. Bridle and reins, Murphy's Soap and Oil, Meguiar's Gold Class Rich Leather, Weatherman's Leather Conditioning Wipes, soapy water, sponge, and rag. Procedure. Get the bridle, and then leather cleaners, and then rub the cleaner onto the bridle with the rag or sponge, and then see what one cleans the best. Note. Before, the bridle was dirty and needed to be cleaned. During, the cleaners were working well and made a difference on how the leather felt and looked. After, the Murphy's Oil was the best and made the leather the most supple. Conclusion. In conclusion, all of the leather cleaners were good, but the Murphy's Oil was the best and made the bridle the most supple. The Weatherman's wipes made the bridle dry, and the soapy water made it wet, and then when it dried, it made it stiff. Then, the Meguiar's Rich Leather cleaning was the second best out of the four. And then the before and after.
Hi, what I'm doing my science fair project on is hydro dipping versus painting. My question about it was, is it quicker to paint detailed designs on objects using hydro dipping or painting? I wanted to do this just because I've always wanted to try hydro dipping and just see how long it takes and see if it was a quick thing to do. If it's a thing that you can do a lot and it's not so hard, which with painting I have a lot of experience because I do it all the time. Then the research and information I did about hydro dipping was hydro dipping is the process of transferring paint that is resting on the surface of water onto an object through dipping. So what I mean by this, it's you get water, a bin with water, and then you spray paint on top of it, a couple colors or whatever, and then you just dip the object in. Then another one is, it is easy to do and gives colorful, cool designs. And the process uses spray paint, obviously. Then about painting is you can create your own specific design with paint. Painting uses paintbrushes and paint, acrylic paint or oil-based paints. And I used acrylic paints because that's what I normally use. My hypothesis was hydro dipping a mason jar will be quicker than painting a mason jar with detailed designs. I thought this just because all you do is dip it in, and then with the painting, I didn't want to be too basic, so this is my painting one. and I didn't want it to look like, I didn't want to just paint it like a plain color because I thought like it'd take so much less time. So yeah, then this is my hydro dipping one. I used different colors too. The materials I used was 2 mixer jars, 1 plastic container, some water in a bin, spray paint, and a stick to like mix the materials together, or like mix, yeah. Then acrylic paint, and I used a bigger paintbrush, and I used a timer to see how long it would take for each one, to see which takes like less time or more. My procedure was gathering all the supplies needed, fill a container with water, add spray paint to water, dip the mason jar in the paint and water. Chase, please stop. Grab other mason jar and hand paint. Then time both procedures and record the time it takes to paint both jars. So I did time both of them. Then my conclusion was the hydro dipping took less time than painting, like as I thought. Then painting took 3 minutes and 5 seconds, and hydro dipping took 2 minutes and 38 seconds. So they're pretty close, so not too far apart. Then hydro dipping was fun to do and creates cool designs. I would definitely do it again because like you can do anything and it just creates a cool like design. Then the notes I had were, before I was thinking the hydro dipping was going to be faster than painting because all you do is dip in colorful liquids. Then I actually realized that you do have to add a lot of layers of spray paint so it's not like thin. Then hydro dipping was pretty quick. All I had to do was add spray paint to my water and dip it in the jar. I painted the second jar as fast as possible. And then I also realized when you're doing it that you can't get like water on top of the spray paint or it will get messed up. And then the hydro dipping was quicker than the painting. Even when trying to paint fast, both were fun to do. I enjoyed it. And then right here I have some pictures. This was me painting. This is the colors I used. I used like a dark blue, light blue, and a white. So I was painting this mason jar, and then this was me hydro dipping, and with this I used like a white and like a turquoise and a darker like blue. And I just mixed it together.
Okay, so this is my science fair. It's called Strongest Sandcastles, and it is for trying to find the strongest sandcastle, of course. I'm doing it with dirt, sand, and water, seeing which mixture is the best. We're doing different percentages of it. So yeah, my question is, what sandcastles will be stronger if I let them dry for 2 days, then crush them with a rock from 3 feet high? So my supplies that I'm using I will need dirt, water, and sand. I'll need a piece of paper for my recordings. I will need a mixture tool, a place to have the sandcastles dry, which is in my backyard where I do pretty much everything. So my hypothesis is, if dirt, sand, and water are mixed together, it should make a solid after drying. Then they should be stronger than just sand with water or dirt with water. I think that if I use an equal amount of all the products, that would make the strongest sandcastle. So the procedure I'm taking, I'm going to pour 33% water, 33% sand, and 33% dirt in a bucket. Then 50% water, 50% dirt, and 25% sand. Then 25% water, 40% sand, and 35% dirt. And this is all going to be put in a bucket. I'm going to stir the mixture so that they're getting hard to mix. I'm going to take them out of the bucket and let them dry for 2 days. Then I'm going to drop a rock from 3 feet high with a tape measure. I'm going to be measuring how high that is with a tape measure. Then I'm going to observe how much damage is done to the sandcastle by the rock. Before, they were wet and slushy like melted butter, and they were definitely not done drying because they just started. During, they got a little harder and a little harder each time an hour passed until a 2-day drying mark came. After the sandcastles dried for 2 days, I crushed them with a rock, and they crumbled, and one of them stood strong. My conclusion, I was right. I thought the first sandcastle would be stronger with 33% water, 33% dirt, and 33% sand, and the other sandcastles crumbled, and this one stood strong. Okay, so here are some pictures. So this is before. So this one over here, this big one, that one, had all equal amounts. This small one over here had too much water and not enough dirt and sand. And then this medium-sized one over here, he had too little water and not enough, and too little water and too much sand and dirt. Then over here, the big guy, he stayed and stood up strong. The two smaller guys, they crumbled to pieces. So I hope you liked my science fair, and I hope you liked it.
Is a lemon battery better than a potato battery? Let's see. Is a lemon battery better than a potato battery? I really wanted to know because I just love batteries and how they work. So I found out that potatoes deliver more watts. The potato is actually, or lemon, is not the battery. It's the electrolyte. The copper attracts the electrodes like it wants to, kind of eat it, sort of. And then the zinc kind of wants to give away the electrodes. And I actually found out that the battery actually lasts till there is no more juice. I am going to use a potato, a lemon, an orange, and a strawberry as my batteries. I picked a strawberry because I thought the sweetness would be maybe a good conductor, and the orange, the citrus, the lemon. And I believe that a potato is a better battery. I would be very surprised if the lemon, orange, or strawberry does better, because I found it because the potato delivers more watts. I need 1 potato, 1 lemon, 1 orange, 1 strawberry, a galvanized nail, copper penny, and a voltmeter. So first, you get a potato, lemon, orange, and strawberry as the batteries. You get a galvanized nail and copper penny for the conductors. You insert the penny in the middle of the fruit or potato, and then you insert the galvanized nail 1 inch away from the penny. But don't let them touch, because that will lead to a short circuit, and it will not be good. And you attach the penny and nail to the voltmeter, and then you write down results, and then you just repeat. So for the potato, I got 0.91 volts. For the lemon, I got 0.73 volts. For the orange, I got 0.83 volts. And the strawberry, I got 0.12 volts. I am very surprised about the strawberry because I thought it would have done better. My conclusion is my hypothesis was correct, because I guess that potatoes were better batteries. They connect 91 volts and lemons connect 73 volts. Sorry, that was a little. So that's what I have.
Mentos by Brody Randazzo. Question: will more Mentos make the spray go higher? Research and information: you can only use Diet Coke. Typically more Mentos means the spray will go higher. Hypothesis: if I put more Mentos in the Coke bottles, then the Coke will spray higher. Materials that you need: Diet Coke, Mentos, flat ground, pencil and paper, and a measuring tape. Procedure: first, put 1 Mentos in 1 Coke bottle. Mark the peak of the spray. Repeat steps 1 and 2, this time using 3 Mentos. Repeat steps 1 and 2, this time using 5 Mentos. Take notes while this is happening. Watch the spray go sky high. Clean up the Mentos in Coke bottles. Note: before the Mentos are in full form, we are using 17-ounce bottles of Diet Coke, and the bottle is full.
right away after you put the Mentos in, it explodes. Here's my videos and my photos. And the first Coke bottle with the 1 Mentos that I put in, it went 10 inches high. With 3 Mentos, it went 15 and a half inches high. And with 5 Mentos, it went 22 inches high. Conclusion: my hypothesis was correct. The more Mentos, the higher the spray. With only 1 Mentos, the spray was only 10 inches high, but with 5 Mentos, the spray went up to 22 inches high.
Hi, my name is Harper Sternberg, and I am here to conduct my experiment between yogurt and ice cream. Now, have you ever been told that you can't have any ice cream to have a healthier option like yogurt? Well, I know I sure have. But I'm here to show you today that yogurt has just as much sugar as ice cream does. Now, if you see here on my poster board, this is my ice cream and this is my yogurt. That the yogurt has a sky-high sugar content. Up at the top here on the Greek gods, it has the most sugar out of all my ice creams and yogurt. And it's a household favorite in my family and many families. After that, there are some other favorites, like Yoplait and Tillamook, that also have a sky-high sugar content. And other yogurts like Wee and Noosa, that might not seem like it has that much sugar, but compared to my ice cream, they're equal amounts. Now it's time to take a look at my ice cream. With my ice cream at the top here, we have Thailand ice cream, which might seem like a lot of sugar, but compared to some other ice creams like Wee, Yoplait, and Tillamook, this doesn't even have as much. You might be like, Harper, it's just vanilla bean, but we have some other fancier flavors. As you can see here, it doesn't have that much sugar. Even with some other favorites that I have, like Tillamook, Ben & Jerry's Half Bake, and even chocolate. Look at how little sugar this one has, which is chocolate chip ice cream, compared to some plain vanilla yogurt. Now, as you can see, proving my experiment point, they have equal amounts of sugar. If not, yogurt has more. Now, next time a parent or guardian tells you to maybe choose yogurt over ice cream, maybe you should choose ice cream. Signing off, Harper Sternberg.
Ice by Hyla Van Kirk. My question was, will ice stick to string? Research and information. If you add salt to a block of ice, its molecules will start wiggling more. Eventually, they move around too much to stay stuck together, and the ice melts, turning back into a liquid. Hypothesis. Does it work with salt, sugar, and baking soda? We will test that out. My thought is that it will only work with salt. I think that because salt has bigger particles than sugar and baking soda. They are more on the dust side. Materials you will need are salt, baking soda, sugar, string, ice cube, and optional is cups and bowls. Procedure. Get a block of ice, gently set the string on the ice. Sprinkle salt on the ice, lift the block of ice up by the string. Notes. Before I did this, I thought maybe it wouldn't work. The ice started melting on the string, then I added the salt, and it was almost like the salt became a part of the ice. It worked. I was so surprised. Conclusion. It worked. I couldn't believe it. It worked with the salt and sugar. I did not expect it to work with the sugar, and it didn't work with the baking soda because it just melted. And yeah, that's it. My question was answered, and the ice did stick to the string, so it worked. The only thing that I didn't think that would work was the salt, the sugar, and the
baking soda because there are tinier particles than the salt. So I didn't think that would really work, but the sugar actually worked, just the baking soda didn't. The baking soda just melted on the ice. And yeah, my question was answered. It did work.
Hi, so this is my science presentation. Paper, N95, or fabric? Which would hold the most water? By Ava Lily Ashworth. My question was, would a fabric mask or a paper mask or an N95 mask hold the most water? So for my research and information, I found out that the paper mask was hard to breathe in, but that means it does not let as much air in or out, so that means water is going to have a hard time getting through. Paper masks are used and meant mainly for hospitals, so that means they have to be super protective so air, spit, or germs don't get through. So water might not get through as well, because water is like sneezes or coughs. And the fabric masks are comfortable masks. Some people even make them, and they are reused. And if they are reused, they have to be washed. And after every use, I think that wears down the fabric. So I think the fabric mask will let out the most water. And finally, with the N95 mask, I think that the mask will hold the most water because this is the best medical mask. And so I think that means the water will have trouble going through it. And my hypothesis was like that. It's just like, I think that the paper mask will hold more water and let out less than the fabric mask. I think this because paper masks are used for hospitals. That means they have to be thick so no bacteria or coughs can get in or out easily. And usually doctors don't wear fabric masks in the hospitals. I think that means paper masks will have trouble letting water out, because coughs have a bit of liquid in them, but the mask does not let out coughs out, and water is liquid. Fabric masks get wet when you sneeze, so I think that it will let more water out if the mask is already wet. That is why I think the paper mask will not let out as much water or let it flow through than a paper mask will. But then I think that if you would compare the paper mask to the N95 mask, the N95 would hold more water because it's even more safe than a paper mask. I think that it would be harder for water to flow through because coughs can get through a paper mask easier than an N95. That is why I think the N95 mask will hold the most water. My materials were 1 measuring cup, 1 bowl, a timer, fabric mask, paper mask, N95 mask, just normal writing paper, tape or skewers, water, and a pen. My procedure was, first I will fill up a measuring cup with 3 cups of water. Then I will set a 1-minute timer and pour the water through the mask with the bowl under the mask without spilling water over the sides of the mask. Then I will stop pouring when the timer ends. Then I will measure the water that is in the bowl. I will do that procedure to each mask separately, and then I will see which mask has the least amount of water in the bowl. My data and observations were the fabric mask. I noticed the fabric mask let out more water through the mask. It let out 2/3 of a cup of water, and the paper mask did not let out any water. Therefore, the paper mask held the most water so far. The N95 also didn't let out any water flow through. Because of this, the N95 and the paper mask both had the same results. And for my notes, I predicted that the N95 mask was going to hold the most water, and I started to see that I was right, but also wrong, because the fabric mask let out 2/3 of a cup of water. But the paper mask had not let out any water, and you can't get less than 0 cups of water. Therefore, the N95 mask would have to tie with the paper mask, or else the paper mask would win. I realized that the N95 and paper mask held the most water, so my prediction was half right, because they had the same score. They tied. And my conclusion was, now I know that the N95 and paper masks are the ones who hold the most water. My prediction was half right because I predicted that the N95 would hold the most water, and it did, but along with the paper mask. This was surprising to me because I thought the N95 mask would also be the most effective for holding water.
For my science fair presentation, I did a test of conductivity. My question/wondering was, how do circuit boards actually work? And for visual and circuit boards, I got one right here. It's a backup to my gaming computer. And you can find them in stores and on Amazon or something like that. And they go inside of laptops or phones or iPads. And that's what makes them work. Some research I did was I read a couple of definitions related to circuit boards of different words. And I Googled circuit boards themselves. I watched a couple of YouTube videos. I set up a couple of meetings with my uncle and dad to get a better understanding about circuit boards, and I learned how to spell circuit correctly in this process. I spelled it some weird way, but I don't anymore, and that's good, I guess. My hypothesis was, and is, circuit boards are made of conductive materials, so if a material is conductive, then it can be used to complete a circuit on a circuit board or just a circuit in general. The materials I knew I would need was to design and build a large breadboard/circuit board, a light bulb, wire, a couple of batteries, some stainless steel, some copper, aluminum, and some other things to test. I also knew I would need an soldering and some solder. That's how it's spelled, but it's actually pronounced solder. It's basically like conductive welding. It's kind of weird. I also knew I would need a saw and some side cutters. A procedure I followed throughout this project was to get the materials I'll need, build the prototype of the circuit board, test my different materials and see which are conductive and non-conductive, and then write down my results about them. And there's a picture right there, but I also have the hard copy right here in this notebook. Some notes I took were before the experiment, I kind of defined the different materials by categories by gut instinct. I thought copper and stainless steel would be conductive, and the cotton, the banana, and the leather wouldn't. And the aluminum and the fiberglass I wasn't sure about, which is perfect, because that's the test. During the experiment, I learned that the stainless steel mesh, the aluminum, the copper, the banana fruit, the water, and wet leather and wet cotton are conductive, while cotton, leather, the banana peel are non-conductive. And for a little bit of background knowledge that I know is that the pure distilled water is actually a poor conductor of electricity, but the stuff inside non-distilled water, like salts and other inorganic minerals, are electric charged particles, and they're called ions, and those ions really help the water to be able to make non-conductive stuff conductive. And that's pretty cool, in my opinion. And what I learned is that fiberglass works as an insulator, so the circuit board doesn't short, and the copper coating works as a conductive material, so the circuit board actually works. I also learned through research and experiments that both non-conductive and conductive materials are required to make a circuit board, but conductive materials are required to complete a circuit. I also learned how to build my own circuit board and the solder wires to them, which is pretty precision. You gotta be kind of precision with that. In conclusion, conductive materials are required to make a circuit. I've also learned that there are many different conductive materials and properties. You can also add conductive properties such as water to make non-conductive material conductive. And this is some extra videos just to watch, I guess. I guess we could watch just one of them. How long is this one?
Okay. So you've taken your non-conductive materials and what have you done?
I dipped them in water because I wondered what would happen if that happened, because the inside of the banana had like a little bit more juice to it, kind of thing.
And right there you can see the LED is lighting up because of the non-distilled water.
That I've learned that the water actually makes the non-conductive source, like I don't really know how to explain it. Like, it makes it conductive.
Okay.
To summarize it. Cool.
Yeah, well, there's that one. And I hope you've enjoyed my presentation. Thank you for watching.
Hello, my name is Blake Nanakis, and my science fair project is can you see if someone is lying just by looking at them? My question is, can you see if someone is lying just by looking and listening to them? My research and information. So I have looked up online of possible things that could mean if someone is lying, like grooming behaviors, saying too much, using unusual rise or fall in vocal tone, eyes are looking around the room, repeating questions before answering them, and pausing before answering. My hypothesis was I do believe that you can tell if someone is lying just by listening or looking at them because of all the things I found online, and I always thought there was a way. My materials were family member, if that counts as a material, and a phone. My procedure was get a family member, tell them to say truths or lies, tell them 2 questions without them knowing what the question is, record what is different when they lie than when they tell truths, and by then I should see if you can tell if someone's lying just by listening or looking at them. First, I have a truth.
What do you work at? I work at Equinix. How many animals do you have? I have 4 animals.
So that was a truth. My mom didn't look suspicious or anything, and she was telling the truth, so yeah. Next thing is a lie. What is your favorite food?
My favorite food is hamburgers.
How many kids do you have?
I have 5 kids.
And as you can see there, if you were watching my mom's eyes, you could see that they were blinking pretty fast near the end and kind of towards the start. So that was something that could be a thing to tell if it's a lie. Next thing is a truth.
What school do I go to? You go to Tahoma Elementary School.
What is your favorite football team?
My favorite football team is the University of Washington Huskies.
As you can see there, my mom was pretty normal. She wasn't blinking as fast as the lie. Nothing really interesting. Next thing is a lie.
What position at your job do you work at? I'm a technical architect.
What is one of your cat's names?
One of my cat's names is Prada.
Now, as you can see there, she was blinking a lot again, but then also near the end, she was looking away from me. And that was one of the things I found online that could be a lie. And my final thing is also a lie.
What's your first house? If I remember correctly, my first house was in the Dash Point area.
What is your favorite color?
Oh, that's a tough one because I like a lot of colors, but I'm going to go with black.
Now there, you could see she was kind of stalling a little bit and telling too much information near the end when she was telling what her favorite color was. So, and that was also a thing I found on the internet of what could lead to a lie. And before, she was normal, no reason not to be. During, my mom was blinking a lot and looking away from me, making it easy to see that she was lying during those videos. Then after, she went back to work and was normal again, like she would always do. And conclusion, I think there is in fact a easy way to see if someone is lying. It's blinking too much, not making eye contact and looking around the room, and saying too much information. And that's my science project. Hope you liked it.
Taste by me. My question is, how does an appearance of a food or beverage affect what people think it will taste like? Research and information. When I researched it, it said that red color changes the flavor even more than others. And that's the source I got it from. That's the materials I was using. So I use strawberry soda for it, but you can use any type of soda. That's my procedure. I followed the steps and now I'm making a video for it. My notes is the soda tasted like strawberry and it was red, and then I put blue food coloring in it and mixed it up, and red plus blue equals purple. And then the participants tasted grape soda even though it was strawberry. They thought it smelled like grape soda too, which I thought was really cool. There's the strawberry soda in the first picture. Now to the right, that's me adding soda. And here's it seeping into the strawberry soda in the video. Yeah. So.
Grape. I think it's grape soda.
That is one of the participants trying the soda and telling me what flavor they thought it tasted like. So my conclusion is the participants smelled grape soda. Even when they tried it, they thought it tasted like grape, when it really was strawberry. In conclusion, the look of something impacts something taste and smells. So my hypothesis was right.
The Biggest Bubble by Brooklyn Watkins. Question: What bubble gum can blow some of the biggest bubbles? Well, we are going to find out by testing out the following 5 different gums, such as Original Bubble Gum, Icebreakers Ice Cubes, Airheads Gum, Trident Layers, and Bubblemint Orbit. These will be tested by chewing for 1 minute each and recording my findings. Research and information. Well, it's proven that if one gum has more sugar than the other, then it will have a better chance of being bigger. It could also depend on the size of the gum. Maybe it has no sugar in it, but could be a huge piece and blow big bubbles. My hypothesis is that the original bubble yum gum will blow the biggest bubble. I say this because the bubble gum is way bigger than the other gums. My materials that I used were the gum, a ruler, a camera, and a timer. What I did was I got the timer set for 1 minute. I had some help chewing the gum for 1 minute until the timer was up. We blew the bubble and we recorded what we found and measured it. So before, of course, the gum was solid and we were getting ready to make the bubbles, and then during, we chewed it for 1 minute each and then blow. After, we recorded what we found, and then I recorded my information. Conclusion. Overall, I think that the tests were pretty accurate, and I wasn't shocked when the bubble yum was the biggest bubble. Here's some photos. They're not the best quality, but I tried. The Orbit bubblegum was approximately 1 inch, the Icebreakers approximately 3/4 of an inch, the Trident was approximately 1.5 inches, Airheads approximately 1 inch,
and the original Bubble Yum approximately 2 inches. And we have that one for the win. Bye, thank you.
My science fair project was which material absorbs better. My question was, which material will absorb better? My research and information was, after taking a bit of research, I found out that towels are covered in little bumps for the water to go into those, so it allows more water to fit into the towel. And believe it or not, paper towels have them too. My hypothesis was I think that the towel will absorb the fastest because of the bigger space for water to fit. And I think the paper towel will be in second and toilet paper in last. The materials that you need are a towel, a paper towel, toilet paper, a stopwatch, and a cup of water. The procedure is dump the water first, start wiping it up, and once you start wiping it up, start the timer, and then stop it when the water is absorbed, and then repeat it with the other materials. My notes were before there was water everywhere, and then during the water was almost cleaned up, and then after the water was all cleaned up. My conclusion, with all the materials taking a turn, the places were number 1, towel with 3.89 seconds to absorb. Number 2, the paper towel with 4.16 seconds to absorb. And number 3, the toilet paper with 8.03 seconds to absorb. And that was my science fair project.
I did butter as my science fair presentation, and questioned, I wondered if I will be able to make butter. My hypothesis was I thought I would be able to make butter, but I wasn't sure because I saw people doing it and I thought it looked pretty fake, so I didn't know. Materials I used: heavy cream, a little glass jar, clean glass marble, or a really clean rock. Large mesh strainer, bowl, salt optional, and I did use salt. I got the ingredients and supplies. I poured the milk into the jar and started shaking. I kept on shaking. I let it sit for 40 minutes, just out in room temperature air. I kept on shaking. I poured it into the strainer and pushed the milk out with the back of a spoon. I added the salt and made an English muffin and put my butter on it. This one, before, the milk was kind of thick in the jar, but not really. The milk started turning into butter and started getting thicker. The butter was fully formed and was really thick, and there was some milk that did not turn into butter. The butter is like store-bought butter, but healthier because I did not add as much salt and as much salt as they do, or any coloring. In conclusion, my hypothesis was right. I was able to make butter, and it tasted so delicious with a toasted English muffin.
This is Bristol. This is my science fair project, and it is, what is the best paper towel? The question is, what is the best paper towel? My research is that Brawny and Bounty are the top 2 leading brands. Snowsoft is the softest brand. Bounty single roll costs $2.86. Snowsoft single roll costs $2.49. Brawny 2-pack costs $4.99. My hypothesis is that Bounty will be the best brand for absorbency because it feels a lot thicker and more dense. They also call it the quicker picker-upper. My materials are paper towels, water, measuring cup, coins, quarters, blue dye, and a dropper. My procedure is to test absorbance, test strength, compare prices, and then record all the data. My notes were gathering supplies for experiment, 3 different brands of paper towels, colored water to show absorbency, quarters to show strength, getting labels for the video. Bounty looked and felt a lot stronger, and Snowsoft felt thinner and weak. videotaping the experiments as we go along, conducting many tests. All tests were conducted equally. Bounty seemed to be the best. Snowsoft absorbed the water, but then it became thin and it dissolved, releasing a lot of water. And finally, Bounty and Brawny performed better in the test than Snowsoft. In a scientific conclusion, I think that Bounty is the best because of absorbance and strength test. And I think that Bounty is the best because of the absorbency and strength tests, also due to the price. I have all the videos here that you can watch. Thanks.
Hi, my name is Connor, and for my science project, I tried to make a carbon sugar snake. For this experiment, you only need a few ordinary household products, and then light them on fire. So, what actually happens when regular kitchen products catch on fire? You are about to find out. My hypothesis is if the amount of the sugar and baking soda mixture is increased, then the carbon sugar snake will grow bigger because it will have more ingredients to expand and inflate. Most materials needed were already in my house. I needed sugar, baking soda, lighter fluid, sand, pie tins, measuring spoons, and a lighter. I first had to pour the sand in both pie tins and then pour lots of lighter fluid over both. Next, I had to mix my 2 amounts of sugar and baking soda mixture. One called for 1 tablespoon baking soda and 4 tablespoons sugar, and the other for 1 teaspoon baking soda and 4 teaspoons sugar. I poured each mixture into their pie tins and then used the lighter to light the sand on fire. I then watched as the snake started to grow from the heat. It was pretty fun to watch, but it didn't smell that great. After the fire died down, I discovered that my hypothesis was correct. The pie tin with the tablespoon mixture made a bigger snake, while the pie tin with the teaspoon mixture was smaller. I did notice that the teaspoon mixture was growing faster, but in the end it was still smaller than the tablespoon mixture. So, in conclusion, if you are in the kitchen and near open flame, don't let baking soda and sugar anywhere near it, or you will get a carbon sugar snake in your kitchen.
My science fair, which is called shot distance. My hypothesis or question is what shoots farther after shaken up, Coke or Sprite? Well, that's my question. My hypothesis is that Coke will shoot farther than Sprite. After my research and information, I wrote that I think the Coke will shoot farther because Sprite has some water and bubbles, unlike Coke. I know that's not true, but later when I do my notes, I actually kind of have some proof that it's mostly just that. Like I said, my hypothesis is that I think that Coke will shoot farther. My materials were Coke, Sprite, tape measure, chalk, and a video recorder. But never mind. My procedure is first I'm going to get the materials. Second, I will shake up the Coke and Sprite. Third, open the Coke. Fourth, open the Sprite. And I forgot to add measure and record. When I first opened it up, that was when the most powerful shot happened. And the Sprite hit 28 inches, which I thought it would shoot a lot farther, but it didn't. And the Coke shot 31 inches. I thought the Coke was gonna shoot like 50 inches and the Sprite would shoot 40, but I was wrong. But my hypothesis was correct. that the Coke would shoot farther, and the Sprite doesn't have any sugar like the Coke does, so the sugar might have been that 3 inches for the Coke that beat the Sprite. And during the action, I noticed that the Coke was way more fizzed, and it was like a whole light brown while the Sprite was just normal. And I thought that since the Coke fizzed up, it had more air ready to come out of the can. So after I thought about why the Coke shot farther than Sprite, I instantly jumped to conclusions without even looking at the materials that were listed on the Coke and online. And I think of Sprite as just water with some sweeteners, but Coke as a real soda, like that has sugar and fizzy powder or something like that. After looking at it, I was kind of right that Sprite is kind of just water and bubbles with a little bit of sweetener. And I did a graph. About basically what has what in it. And the Coke has 90% water, same with the Sprite, 2% artificial flavors, and so basically the added sugar was 10%, and that's not very much considering how much water is in it. So basically both of these are healthy in their own ways. In conclusion, Coke shoots farther than Sprite does. That's basically what my whole science fair was about.
For my science project, I did Touching Your Face by me, Eliana Ricker. My question was, how many times do people touch their face a day? And does it depend on what you're doing, gender, or age? I wondered about this because everyone's different, and I wonder if that depended on touching their face. I found out that people usually touch their face 15 to 16 times an hour, so I knew my answer would be around that. But then another website that said that you usually touch your face 13 times an hour, and this made me wonder. So I wanted to see which website was really telling the truth. My hypothesis was, I think kids touch their face more because they're more active or they play a lot. And like I said, I thought this because they're very energetic, more than adults. And I wanted to see if that depended of how much they touched their face. For my materials, I need, obviously, paper, 4 people to study with, which I think, a good system, and a pencil, obviously. For my procedure, I asked my people to study permission. Then I did 1 hour for each person. I put a tally for every time they touched their face, and I multiplied that by 12 because that's how many hours you're usually awake in a day. And I also listed the things that they were doing. I had one more person, my grandpa, but I didn't get to get a picture of him. From my data and observations, I came to a conclusion that my dad, working at his computer for work, touched his face 528 times. He touched his face 44 times an hour, and I multiplied that by 12. My grandma building Legos touched her face 108 times, and that was 9 times an hour, and I multiplied that by 12. My brother building Legos touched his face 12 times an hour, multiplied that by 12, and got 144. And my grandpa outside and eating lunch touched his face 204 times, and he touched his face 17 times an hour. I thought kids would touch their face more because how active and jumpy they are. I thought adults would do it less because they're older. Also, I expected numbers per hour that would be 13 through 16. but I thought it would be 13, 16 times an hour because that seemed about right. But when I did my results, it surprised me that it was a little bit different. And as results were being finalized, I was shocked that my family touched their face so much during the process. I was becoming to understand that it mostly matters what the person's doing. So gender, age didn't matter. It's just what they were doing. In the end, I had all the results and the numbers were high. It seemed that people doing their normal activities touched their face the most. Gender or age did not matter at all. I was surprised by this because I thought kids would touch more, but they actually didn't. And my brother is the kid I studied, and he was actually in the lower two. In the end, people touch their face 500 to 100 times a day, depending on what they were doing. So if you're doing a lot of things with your hand, you would probably touch your face last. But if you're doing like work like my dad was doing, or eating lunch, or just outside, you would probably touch your face more. I hope you enjoyed, and I had fun doing this process.
Hello, my name is Diana, and the experiment I'm doing is cleaning microwave. I chose that experiment because, well, my mom kind of helped me choosing it. She thought it would be helpful, which it was, so I just decided to go with it. My question was, which of the following products will clean best? Baking soda and vinegar, lemon juice, or Coca-Cola? Well, Coca-Cola, I just saw so many cool videos of people like washing things and it worked very effectively. So I decided why not? And then when I did research, I saw that a lot of people use lemon juice too. And I also saw a lot of people using baking soda. And well, vinegar, I know that it makes an explosion, baking soda and vinegar, but it actually didn't make that much of an explosion. My research and information. I know that some of the most common methods are baking soda, lemon juice, and Coca-Cola. Hypothesis. If you clean the microwave with Coca-Cola, then it will clean best but take longest. Well, that's just what I saw in like the videos I looked at. So that's my hypothesis. My materials needed. Cup, cola, vinegar, water, baking soda, and sponge. Procedure. Method 1. With cola. Grab a sponge and pour some cola on it. Rub the microwave on the inside. Wipe off with a clean wet sponge. I also kind of had to let it dry because, well, I did not want a wet microwave. And also make sure it's a clean sponge that you use again to wipe it off, because if you don't use a clean one, then your microwave will still be dirty, and we don't want that. Procedure. Method 2. With vinegar and baking soda. Mix baking soda and vinegar. I know that is probably gonna make an explosion, but just try to add not too much vinegar. Grab a sponge and pour some mix on it. Rub the microwave on the inside. Wipe it off with a clean, wet sponge. Also, be very careful when you're rubbing the mix on the microwave, because you don't want to get baking soda or vinegar into the parts that are where the light is, or in other places like that. Method 3. With lemon juice. Pour lemon juice into a cup. There you might also want to add a little bit of water, because I don't think you have that much lemon juice at home. Microwave the lemon juice for 1 minute. I microwave for 1 minute, but it also kind of depends on the temperature your microwaves at. Wipe off with a clean, wet sponge. Compare the effectiveness and time of the methods. Well, that's data and observations. Notes. Before. The microwave was kind of dirty. It was oily and greasy. It had oil spills all over it. It looked hard to wash off spills that already dried if I use only water. It was kind of disgusting because it was a lot of all the different splatters of food that we microwave. Lemon juice. It made popping noises. Well, that's at least what I heard from the microwave, since I was not inside the microwave and I could only hear. It also smelled like lemons. Yeah, it smelled a lot like lemons. It wasn't the best smell, I would say. I honestly did not really like that smell. So, yeah. Coca-Cola. I didn't want to hold cola in my bare hands, so I had to put gloves on. The cola bubbled when it came in contact with the oil. I don't know why I did that, and I did not expect that. Baking soda and vinegar. I liked when the foam came up when I mixed the two ingredients. The process was satisfying, except I did like cleaning the baking soda and vinegar off, like when I was wiping it off with the wet sponge. That was not very satisfying. Lemon juice. The floor of the microwave was covered with lemon juice. There wasn't much of the juice on the sides. After I wiped the juice off of the microwave, there were still some spots left. It could have been better. Yeah, I think it didn't clean as well as all those websites said. Coca-Cola. It took very long to wash the microwave. I expected it to be shorter. The microwave did not end up clean, but now the microwave did end up clean, but now I can't reuse my sponge because it's dirty from the cola. Yeah, I couldn't wash the cola off of the sponge, so now I don't have a sponge. At least I don't have that sponge. Baking soda and vinegar. I thought this would take much longer. I feel like this method was most effective. There was absolutely no oil or dirt left. Conclusion. My conclusion is that the baking soda and vinegar clean best, but the lemon juice is the fastest. The cola took second place. It cleans good, but not the best. It also didn't take too long, but could have been shorter. Yeah, and that's a picture of the microwave after the baking soda and vinegar. It looks pretty shiny and clean to me.
This is my science fair project by Eliza Doherty. And my question is, does the temperature of a glow stick affect how bright it is? The supplies needed in this situation were warm water, a fridge or a cooler, a thermometer, a dark area, a camera, and glow sticks. The steps in this project were to put 3 glow sticks in a fridge, heat up water, put 3 glow sticks into that water, leave 3 glow sticks in a room temperature area, wait 30 minutes, take the glow sticks out, and see which pair of glow sticks glows brighter or less than the others. The steps for the room temperature glow sticks were to take 3 glow sticks, leave them in a room temperature area, activate them in a dark area, and record how bright it is. This is how bright they were. The steps for the colder glow sticks were to put 3 glow sticks into a fridge, wait 30 minutes, take them out of the fridge, activate them in a dark area, and record how bright it is. This is how bright they were. The steps for the warm glow sticks were to heat up glow sticks in water that's 140 degrees for 5 minutes. Take them out of the water, then put them into a dark area, activate the glow sticks, and see how bright it is. This is how bright they were. In conclusion, I have learned that the answer to the question, does the temperature of a glow stick affect how bright it is,
And the answer to that is that the hotter the glow stick is, the brighter it will glow. Although a colder glow stick won't glow as light as a hotter one, but it will glow lighter than one at room temperature.
Okay, this is my experiment. I am doing bubbles, and so this is my question: which soap will work better? And then my research and information is a bubble is basically an extremely thin film of soapy water. And yeah, that's the whole thing of the research and information. And then my hypothesis, I think dish soap will stay in the air the longest. So that's my prediction, that I think the dish soap will stay in the air for the longest. And then my materials that I have is 4 types of soap: a bubble wand, bowls, a timer, pencil and paper, and a regular bubble mix. And then my procedure is I will set up the 4 different kinds of soap, blow bubbles with each soap, record how much time the bubbles stay, see which one is the winner, and research why that soap won. And then my notes is my before is I made a prediction that dish soap was going to win, and I got my supplies ready. And then during, the bubbles were in the air and falling to the ground. And then my after is I recorded each of the bubbles and decided which soap was the winner. And then my conclusion is, for my experiment, I tested which bubble would win after testing the 5 different soaps. In the end, the hand soap was the winner, and my prediction was that I thought the dish soap would win, but I was wrong. And then my 10th slide is that, and then this is all my videos. I'm only going to show one, or actually I'll show all of them, I think. I don't know which one is which, but yeah. So that's the first one. My mom, that one, I know that one was the hand soap, because that one took a while to do. And then this is the next one. The worst one was probably, I would say, the body wash, I think. Okay, and then this is the next one. I think that was the body wash, because it barely worked. So but it at least still made it. And then this is my 5th one. My second best one was probably the actual bubbles. So yeah. So those were all my videos, and I hope you like my presentation.
Today my science project is about what's the dirtiest. Let's take a closer look at what I'm trying to test. I'm trying to test what would be the dirtiest. Bottom of a shoe, a keyboard, a dog's mouth, a human's mouth, water from a creek, a toilet seat, a 3-year-old's hands, a cell phone, rainwater, and a school doorknob. What will be the dirtiest? I am very curious to find out. Hypothesis. If all my tests are successful, then I think the school doorknob will be the dirtiest and the creek water will be the cleanest. I thought that the school doorknob would be the dirtiest because everyone touches it, and even though it might get sanitized, people use it a lot, and on people's hands there are germs and it can spread. And so I thought that maybe there would be a lot of germs on there. And the creek water, because it's out in nature and the water is fresh, and I thought it'd be the cleanest. Okay. Research. When testing materials to see what is the dirtiest, take the cotton swab, make sure either the item you're testing or the cotton swab is damp, then rub the cotton swab on that object. After you do that, then rub the cotton swab on the agar plate. Wait 1 to 2 days to find bacteria growth. After I waited 1 to 2 days, sure enough, I found bacteria growth, and it was pretty dirty. Materials. 1. Agar plates. 2. All the things to test. 3. The Petri dishes. 4. Cotton swabs. And 5. A good place to let them sit and grow. I figured out that when I put them in the sun, because that's where I originally had them sometimes, that they would start like evaporating, like the water would, that I got because I had to get the cotton swab wet. And so I put them back under the shelf or on a table, not near a window. Procedures. 1. Make a list of all the items being tested. 2. Start swabbing the test subjects. 3. Wait until I start to see bacteria growth. 4. Analyze which one has the most and least. And 5. Record the data. Notes. First, I gathered up all my materials and got ready to start testing. Making sure my cotton swab was wet, I rubbed it on the item I was testing, which was at the time the keyboard. After rubbing the object, I then got the Petri dish and agar plate and rubbed the cotton swab on the agar plate. A few days later, after I had gotten my tests and waited 24 to 48 hours, I saw bacteria growth. Each day I would go to check, and there would be more. Let's watch a quick video of me testing one of my objects, which was the keyboard. Gotten the cotton swab a little bit wet, and now I'm going to test the keyboard. Okay, let's look at some of the bacteria. Alright, let's take a closer look at some of this bacteria. Let's start with number 1, a dog's mouth. Next we have 2, a keyboard. 3, bottom of a shoe. 4, a human's mouth. 5, water from a creek. 6, a toilet seat. 7, a 3-year-old's hands. 8, a cell phone. 9, rainwater. 'And last, 10, a school doorknob. It's actually the one to get into the office. Let's see which one is the dirtiest. I hope you got a good look at that bacteria that I was growing. Okay, let's go to the next page. Conclusion. In conclusion, the 3-year-old's hands were the dirtiest, and the human's mouth was the cleanest. I was very surprised that the human's mouth was the cleanest, because I thought the water from the creek would be cleanest of them all. But, sure enough, the 3-year-old's hands were the dirtiest, and the human's mouth was the cleanest. I hope you enjoyed my science fair project about what was the dirtiest, and bye!
Hi, my name is Kelsey, and I'll be sharing my egg substitutes performance. This is going to be my science fair experiment. A question: how do my egg substitutes perform differently in cornbread as a binder and in cake as a leavening agent? How will the banana and the yogurt substitutes act differently? What is the outcome when I simply use no egg? What about taste? My research and information. Slide 1, my egg research. Eggs help the leavening in cake because they help trap air pockets in food, causing it to expand when in the heat. This helps it to rise and to be light and fluffy. Cakes or cupcakes are a good test for leavening. Also, Eggs help the binding because it helps combine the ingredients and hold them together, which is another way to say that it helps it from falling apart. Cornbread is a good test for binding. Research and information slide 2, yogurt research. Yogurt helps cakes swell and rise. Also, you want to use regular yogurt to get the best flavor, and you need 1/4 cup for 1 egg. My banana research was, when you use a banana as your egg, it may have a hint taste of banana. Also, when you use a banana, it will make it dense and moist, and when you need half a medium-sized banana for 1 egg. My hypothesis, my binding hypothesis. I think when I use the banana for my cornbread, it won't crumble as much because it is dense. I think when I use the yogurt as a substitute, it will be extra crumbly because it will be moist/wet. My leavening hypothesis. I think my cupcakes will be more dense when I use the banana and will not rise as much. I think since the yogurt is so wet, the cake will be sticky, and it will affect how much it rises. My materials. So my cornbread, aka binding. 4 cornbread mixes. I used Jiffy cornbread mix. Mashed bananas, half a medium size. Plain yogurt, 1/4 cup, 1 egg, and milk. Cupcakes. For leavening, 4 cake mixes. Use Betty Crocker's yellow cake mix. Mashed bananas. I used 1½ medium size. Plain yogurt, 3/4 cup, and 3 eggs. Oil and water. My procedure. This is me making my some cake, a cake box. So for the binding, I prepared my cake mix, then I baked it and cooled it. I tested it, I recorded my results, and I presented my results. And here's a little note. I made 4 batches overall, 1 for egg, no egg, banana, and yogurt. And then for my procedure for my leavening, I prepared cupcake mix, I baked it and cooled it, I tested it, I recorded my results and presented my results, and then I also made 4 batches for that. Egg, no egg, banana, and yogurt. What my batter looks like. So these are just some photos I took. So this is the cake batter over here, and this is the cornbread batter. So these are just it, and then I have little labels and arrows pointing to the ones that it goes to. These are some photos I took while I was making the mixes. Okay. And then these are my cornbread and cupcake appearance. So right here I have what the cupcakes look like next to each other. So this is the no egg, banana, yogurt, and egg. So these are for the cupcakes. And then for my cornbread, I have egg, no egg, yogurt, and banana. So that's those 2. My data and observations. Heights for leavening. So how I got these are the steps I took to find the height of my cupcakes. I put a toothpick in it. So I put a toothpick in the cupcake, just like the soda shows. And then marked where on the toothpick the cupcake ended, measured it, and wrote it down. So each batch, so for the egg batch, I had 6 cupcakes. For the banana batch, I had 6. Yogurt batch, I had 6, and no egg, I had 6. So I had 6 overall, and then I combined the each section, and then I found how much each one was in millimeters, and I got the averages. So the egg average was 47 millimeters, the banana average was 40 millimeters, the yogurt average was 37 millimeters, and the no egg average was 40 millimeters. That looks like. Doesn't look like the yogurt did that well compared to the egg. It's 10 millimeters less. And the banana is the same as the no egg average compared on the leavening side. So these are some videos I made for while I was testing my cornbread. So this is testing the binding of the cornbread. I'm not going to show you the videos but my test 1 was just simply crumbling it in my hand. The test 2 was shaking the pan with the cornbread split in half and face down to see if it broke apart well, and my testing results were, I think the banana and the yogurt substitutes were great binding agents, and in the no egg shows how much the egg does for the cornbread. So I definitely do think that seeing them definitely helps on which one's which, and they were well, and I definitely think they're moist too. So, okay, sorry, I had to kind of fast forward like that. Okay, so for my cornbread taste test and my cake taste test, I'm not going to show you these videos either, but they're just going to kind of go over how they tasted, and I have this little box here to show how they tasted. I thought that the ones that I used the banana as a substitute, it tasted a lot like banana bread, and I definitely agree. It was good, it was moist, but it was definitely a taste of banana bread. The yogurt cornbread and cupcake didn't taste like yogurt. It was somewhat bitter and didn't taste as good as the egg batches. Although it was good, but it was just plain and you couldn't really taste anything. So there's that. The no egg batter for the cornbread, it was good. It was more sweet, but the cake batter, it just wasn't good. You really need it. And then my conclusion. In conclusion, I think my hypothesis is very close to my results. When making the Jiffy cornbread mix, I would recommend using no egg when you don't have any eggs, or if you can't have eggs because it is good tasting, even though the binding isn't that great. When making cake, I recommend the banana as your substitute if you don't mind a banana taste. If you do, then I recommend the yogurt substitute. I enjoyed finding what the different impacts were with the egg substitutes, yogurt, banana, and simply no egg. I would say this project helps see what an egg does and what its substitutes do too. And then here's some of my notes. Times I mixed the batters, how I checked the cornbread and the cake batter, and the size of mixes I used. And then just a little bullet point on how many boxes I made. Thank you guys for watching. And yeah, that was my science experiment for egg substitutes performance.
Color Explosion by Brooklyn Harders. Question: how and why does the water and the oil separate when they are in the same jar together? Research and information. Scientists say that if you put the Alka-Seltzer in the water and oil, the Alka-Seltzer makes a gas called carbon dioxide. Also, the carbon dioxide makes bubbles with the colored water and they float up to the top. Hypothesis: if I put 2 tablets in the jar, will it do the same thing as 1 tablet? Materials: 1 to 2 cups, 2/3 cups of oil, 1/3 cup of water, 15 to 20 drops of food coloring, and 1 to 2 Alka-Seltzers. Procedure: pour the 1/3 cups of water into the jar, then put the 15 to 20 drops of food coloring in the water, then mix. Then put the 2/3 cups of oil in. Then once you are ready to put the Alka-Seltzer in, and watch. Notes. Before the experiment, it looked kind of weird because the water and oil were separated. During the experiment, we put the Alka-Seltzer in and it started to bubble up. After it was done, it looked similar to how it looked in the beginning, but tiny little pockets of oil were rising to the top. Conclusion. In conclusion, my hypothesis was kind of right, because when I put the second seltzer in, it kind of stayed the same, but it was a little more powerful. What I thought it was going to do was make like 2 times the bubbles that were already in there. Bye!
Hello and welcome. I'll be sharing my slideshow presentation. My slideshow presentation's name is Reactions by Jack Hoyt. My first question was that what if you mix baking soda and Coke together? Will have a chemical reaction or no chemical reaction? And my second question was, what if you mix Diet Coke and Mentos together? Will have a reaction? And lastly, my last question was, what if you mix vinegar and baking soda together? Will those have a chemical reaction? In 2005, a science experiment, which was the Coke and Mentos, became worldwide, and then in 1999, a professor at the University of Illinois in Chicago, Lee Marek, demonstrated Diet Coke and Mentos on The Late Show with David Letterman. I know if bases are mixed, bases and acids are mixed, they cause a chemical reaction. So I know if I mix Diet Coke and baking soda, it will cause a chemical reaction because Diet Coke is an acid and baking soda is a base. Then if I mix vinegar and baking soda, I will also have a reaction. Because vinegar is an acid and baking soda is a base. Lastly, if I mix Mentos and Coke, it will have a chemical reaction. Procedure I'll be doing for my experiment was mix Coke and baking soda together, and then mix vinegar and baking soda, and then mix Coke and Mentos. My materials was baking soda, Diet Coke, vinegar, Mentos, and including a disposable plastic bottle. My notes were Diet Coke is an acid, baking soda is a base, and vinegar is an acid, and baking soda is a base. Diet Coke is an acid, and Mentos and both together create carbon dioxide. My data and observations were that when I mix my baking soda and vinegar together, they created a fizzing effect. And then when I mixed my Coke and Mentos together, it created a geyser effect. The same thing with the baking soda too with the Coke. In conclusion, I found out that vinegar and baking soda create a fizzing effect. Baking soda and Diet Coke shoots up. The reason why this happens because carbon dioxide, it will also happen because of it becomes carbon dioxide. It will also happen to Mentos and Coke. It will make a geyser because Mentos and Coke make a geyser, and those two make carbon dioxide, which that's why it shoots up. Same with Diet Coke and baking soda. Well, thank you for letting me share my science project. And I will have 3 YouTube videos posted for my data and observations. So just my first one's called the first experiment, which all you have to type is that, and then in this one it's going to be a second experiment, which I don't know what happened just now. Okay, this one will be second experiment, and first and second experiment, and then lastly my third video will be called third experiment. So, and that's it, but thank you for letting me share my science presentation. Thank you, and bye.
Mrs. Bristol. This is my science experiment, toy car and surfaces by Ethan Schlup.
So my question is, which surface will the toy car go farther on? And I didn't have any research because I already knew how to do it, and I didn't need anything for research. And my hypothesis is the toy car will go farther on the hardwood floor because the hardwood floor doesn't have any cracks. The hardwood floor also doesn't have carpet. And my materials are toy car, hardwood floor, driveway, carpet, and measuring tape. And my procedure is put the toy car on the hardwood floor, measure it. Put the toy car on carpet, measure it. Put the toy car on driveway, measure it. My data and observations are: in the beginning, the toy car on the hardwood floor for the first try only went 25 inches. In the beginning, the toy car on the carpet only went 24 inches. In the beginning, the toy car on the driveway for the first only went 27 inches. And here's one of my videos. In the second try, the toy car on the hardwood floor went 33 inches. In the second trial, the toy car on the carpet went 25.5 inches. In the second trial, the toy car on the driveway went only 20.5 inches. And here's another video. After. In the last trial, the toy car on the hardwood floor went 33 inches. In the last trial, the toy car on the carpet went 27 inches. In the last trial, the toy car on the driveway went 31 inches. And here is another video. And then here are some more. Here are the rest of the videos. And then here are the pictures of me measuring it. And my conclusion is that my hypothesis was correct. The toy car would go farther on the hardwood floor. On the first try, the toy car on the hardwood floor went 25 inches. On the second trial, the toy car on the hardwood floor went 33 inches. And on the last trial, the toy car on the hardwood floor went 33 inches. Second, the carpet for the first trial, the toy car went 24 inches. On the second trial, the toy car went 25.5 inches. And on the last trial, the toy car went 27 inches. Also, the driveway for the first trial, the toy car went 27 inches. On the second trial, the toy car went 20.5 inches. And on the last trial, the toy car went 31 inches.
Hi, I am Gabby Gonzalez, and this is my science fair presentation. It has been a bit laggy, so it's going to take a few seconds to load. But I'll put it into presentation mode, and I'll tell you a bit about my project. So basically, I did my project about height, length, and mass. Basically what I did is I made a cardboard car with 4 wheels, and I put it down a ramp and saw how what the distance was between the ramp and the car. And I measured the length, see the difference between if I used bigger wheels and smaller wheels, and the height of the ramp. My question was, does the height of the ramp and the size of the wheels affect the length of how far the car goes? This is just some research and information. You can go to the link, or you can just read the information. You can just pause because it takes a long time to read, and I don't have that much time. My hypothesis is the higher I put the ramp and the bigger the wheels, the farther it will go. The materials I used for this project was 2 straws, a big piece of cardboard, some scissors, I suggest bigger scissors if you're actually planning to do this, tape, a ramp-like surface, and a cup to trace on the cardboard for circles. The procedure I took is, first off, I placed the different sized wheels on the car one at a time, obviously, because I can't do that at the same time. Measured the ramp's height before I did it, let it go, record the data like length, the height, etc., and do that 2 times with the 2 different size wheels. If you see to the left, this is an example of the different size of the wheels. On the top, obviously, it's the smaller one, and on the bottom is the bigger wheel. Before the testing, at first, the wheels weren't moving because I had tested that. So I thought I needed better wheels, but I quickly tested the ramp, and it was that I hadn't used the ramp. Instead, I used a flat surface. So I realized that, and I began my testing. The first attempt, I used the smaller wheels, and I had the ramp at 7 inches high, and I let it go, and it stopped at 1 foot and 4 inches away from the ramp. The second time, I used the same measurements, but for the bigger wheels, and for the bigger wheels, it was 1 foot and 10 inches that time away from the ramp. So I tried the same thing again, but with the ramp at 5 inches height. And for the smaller wheels, it was for 1 foot, and the bigger wheels, 18 inches, or 1 foot and 1 foot and 4 inches. After the test, I realized that maybe the reason that the measurements were so close together was because of the size of the wheels. So maybe next time I could make it larger and smaller so that I could see the difference of the wheels. In conclusion, overall, I think that my testing results were clear, and I realized that I could have made some adjustments to my project that may have made it more clear, but I think I can continue this topic if I'd like, because it really interested me. Because I think it's really interesting the way that if you change the size of the wheels, or maybe the material of the wheels, or how high and low you put the ramp, or maybe even different textures of the ramp, like if you wanted to make it more rough, or smooth, or thinner, or thicker, or stronger, or weaker. You can literally do whatever, and I think that that's so interesting because you mess with one little thing and it affects the rest for the good or bad, which I think is really interesting. So that was my science project. I hope you liked it, and I think I'm going to leave it there. That was Gabriela Gonzalez's, or Gabby Gonzalez, science fair presentation about mass, height, and length. Thank you.
Hi, I'm Ivy, and for my science fair, I have the project of can eggs float with this much amount of salt? The question is, how much salt does it take to make an egg float? And which egg floats higher, farm fresh or store-bought? The research that I have is that for 1 cup, you should add 3 tablespoons, and that should be enough to make the egg float, because eggs have a deeper, higher, bigger density levels than water, which means it goes down. And so knowing how much an egg weighs can be important for knowing what it is. So my hypothesis is 2 tablespoons can make an egg float, and farm fresh floats higher, even in the same amount of salt and water, than grocery bought. The materials you need is 1 cup water, 3 tablespoons, farm fresh egg, a store-bought egg, and a large clear plastic cup. How to do it is you fill 2 cups with 16 ounces of water. Put 1 egg, both eggs in with no salt. Take them out. Mix 1 tablespoon of salt in. Put them back in. Take them out, and you can repeat step 4 through 6 as much as you want to see which one has a higher, less density. Here are all my pictures of data, and what I can see is that farm fresh floats higher than store-bought, which is the white egg. The farm fresh one is the brown egg. Notes that you might need to have before you do this experiment is to make sure the eggs are the same weight so there's no difference. And you can slowly add 1 tablespoon of salt in. Don't throw away. In conclusion, 2 tablespoons is the sweet spot for this experiment, and farm fresh eggs float higher than store-bought eggs, which means they are less dense.
What reacts in water, baking soda or baking powder? By Kai Kaholakula. Question: which will react in water, baking soda or baking powder? Research and information: water at room temperature. Baking powder. Ingredients in baking powder: baking soda, cornstarch, sodium aluminum sulfate, and monocalcium phosphate. Cornstarch. When it is mixed with water, it creates a thick substance. Monocalcium phosphate. It is acidic. Baking powder is generally used in baking or cooking. Baking soda. Ingredients in baking soda: sodium bicarbonate. They are essentially the same thing except that baking powder has added ingredients while baking soda is only sodium bicarbonate. Hypothesis: if I add both baking soda and baking powder into water, I think they will both react because they are both baking sodas. Materials: 1. Baking powder. 2. Baking soda. 3. 2 glass cups. 4. 1 cup of water for each. Procedure: 1. Gather materials. 2. Pour 1 cup of water into each jar. 3. Add 1 tablespoon of baking soda to one jar, then add 1 tablespoon of baking powder into the other jar. 4. Stir up the water with a stirrer or spoon. 5. Wait for 1 minute to see what happens. Notes: Before the water is at room temperature, and we've added the baking soda and baking powder to each jar. During, the baking powder produced some bubbles for a short time, but the baking soda did not react. After, the baking soda has dissolved, but the baking powder is milky-like. This is what baking soda looked like, but not much happened, but the baking soda has dissolved. Baking soda. This is how the baking powder turned out. It reacted and created tiny bubbles. Then it turned into a milky liquid, and the milky color comes from the cornstarch. Baking powder. Baking soda, sodium bicarbonate. Cornstarch. When it is mixed with water, it creates a thick and mushy substance. And that is why people use it to make things like pudding, soup, and other desserts, or food. Sodium aluminum sulfate. It is heat activated, so it helps baked goods rise. Monocalcium phosphate is acidic, which is why when you add baking powder to the water, it reacts and makes it bubble. Sodium bicarbonate, monocalcium phosphate equals bubbles, the reaction. Baking soda, sodium bicarbonate. There are no added ingredients like baking powder, which is why it does not react the same way that baking powder does. Side note: if you add baking soda to vinegar, it will react because it is acidic, just like how baking powder reacts with monocalcium phosphate in water. My conclusion: my hypothesis was incorrect. Only the baking powder reacted, but the baking soda did not. The reason that baking powder reacted is because when you add baking soda, sodium bicarbonate, to something acidic like monocalcium phosphate, a reaction will occur. The baking soda did not react because it is just purely sodium bicarbonate and water, which will not cause the same reaction.
We're going to try to get the fan to spin with this magnet using negative force on the positive force that's already on the magnet, and we need it to turn counterclockwise to power this 2-volt light bulb. So first it would find it, but it's sticking to that, so we want to flip it. And now, but we have if we hold it in a certain angle, it should go. But since the negative force is going against the positive force, and like this right here is the positive force, it wants to connect right there. So it's not going to work.
See, you would really hold it like this, but it's not moving, and it wants to drag it to me instead of pushing it away.
It gets to a center point and wants to drag, pull, and push at the same time, so it doesn't work, does it?
Nope.
We can get it to spin and move a little bit, but
I mean, even if we try to do positive and positive, it doesn't go fast enough.
Right, because to get any type of electrical current out of it, we had to go really fast.
And just doing this, it's 5 volts, 5.5 volts.
So
yeah, if we wanted it to work, we could use our fingers, but we'd have to get a different light bulb.
A smaller voltage light bulb. So experiment is a bust.
Yes.
Hey guys, my name is Ian Rhodes. You probably heard me. Here's my bugs versus food project. Here's my question. Does spinach attract the most variety of bugs? I did some research and found out that some bugs like fruits and plants. And there are 560 varieties of insects in Washington. They're going to love my food. I predicted that spinach will be a big hit with lots of different bugs. I gathered these materials right here. Here's how I did. I got the food, 4 pieces of cardboard, put the food under 3 of them, kept one under control, and checked them for 7 days. Picture time! Setup. Here is me and the materials. Here's the spinach. Here are the oranges. Here's the spinach, bananas. I cover them up in order to protect them, including the controller that has nothing under it. I forgot to check on day 1, but on day 2 I noticed ants on the food, no food or anything else. Note, ants are there, but they don't photograph well. Here are the pictures. Day 3, 4, 5, 6, 2 ants on food. Here are the pictures on day 3. On the days. Day 6, orange ants, bananas, and on day 6, beans got yellow with some socks and a yellow spot millipede under the control. Here are the pictures. There's a yellow spot millipede. Day 7, oranges, ants, bananas, ants, spinach, worm, control cells. A worm show up on day 7 near the spinach. Final data over the week. Here are the final data after 7 days. Final data over a week. Oranges, ants 1. Bananas, ants, slugs 2. Spinach, worm 1. Control, yellow spot and millipede sucks 2. Here's what I concluded. Conclusion. Does spinach attract the most bugs? Variety of bugs? No. Other things I learned about. Ants rule the forest. Cobalt young can attract vertebrates. No food required. Thank you.
Hey, this is my science fair project. It's an at-home lava lamp. My question was, what chemicals, liquids, and other things could make up a lava lamp? My research and information was water and vegetable oil are separated, and the food coloring should go to the water, which making it blue on the bottom if it goes to the bottom, or blue on the top if the water goes to the top. And then the Alka-Seltzer creates carbon dioxide bubbles that should go to the top. And then my hypothesis was, I think an Alka-Seltzer and food coloring, water, and vegetable oil will make one. And then my materials were a bottle, an Alka-Seltzer, and water to pour in, and then vegetable to pour in, and then food coloring. And then I would add the vegetable oil 3/4 of the way in the bottle, and then I'd add water to the neck of the bottle, and then I'd take my food coloring, and then I'd add as many drops as I want. Each drop makes it darker, and then I'd break up the Alka-Seltzers into like 6 to 8 pieces and put it in, and then once it stopped bubbling, I'd put the cap on and shake it and see what would happen. My data was when I add the water and the food coloring in the vegetable oil, it bubbled a little bit, but once I added the Alka-Seltzer into the bottle, like one by one, it was bubbling a lot. And my notes were all the food coloring was in the water below. So the water is below the vegetable oil, and the food coloring didn't go to the vegetable oil. And then during, bubbles started to rise when I added each Alka-Seltzer. The bigger the Alka-Seltzer got, the more bubbles there was. And then after, it was full of little bubbles, and a light blue on the vegetable oil, and the dark blue in the water. And my conclusion was it worked just like a lava lamp. It was colored and bubbles started to rise when I added the Alka-Seltzer. So here's some pictures of, that's when I added the Alka-Seltzer, and then this is when I shook it up after. So yeah, that was my science fair project.
Testing paper airplanes by Leo Ledbetter. My question is, what paper airplane design will fly the farthest? My hypothesis is, I think that the plane will fly further if the weight is in the middle or in the front and back. Also, I think the wings should be hooped up near the body of the plane. Paper airplane number 1. The first paper airplane weighed 16 grams and the range over 3 throws was 197 inches to 201 inches. The weight on this one was distributed evenly. Paper airplane number 2. The second paper airplane weighed 26 grams and the range over 3 throws was 230 inches to 259 inches. The weight on this one was distributed evenly. Paper airplane number 3. The third paper airplane weighed 40 grams and the range over 3 throws was 135 inches to 173 inches. The weight on this one was distributed evenly. Paper airplane number 4. Fourth paper airplane weighed 92 grams and the range over 3 throws was 199 inches and 237 inches. The weight on this one was mostly in the front. Paper airplane number 5. The fifth paper airplane weighed 14 grams and the range over 3 throws was 106 inches to 139 inches. The weight on this one was mostly in the front. Paper airplane number 6. The sixth paper airplane weighed 16 grams and the range over 3 throws was 116 inches to 228 inches. The weight on this one was mostly in the front. Paper airplane number 7. The seventh paper airplane weighed 12 grams and the range over 3 throws was 234 inches to 300 inches. Summary. The first paper airplane weighed 16 grams and it went over, and the range over 3 throws was 197 inches to 201 inches. The second paper airplane weighed 26 grams I threw it 3 times, and the range was 230 inches to 259 inches. Third paper airplane weighed 40 grams. I threw it 3 times, and it went 135 inches to 173 inches. The fourth paper airplane weighed 92 grams. I threw it 3 times, and it went 199 inches to 237 inches. The fifth paper airplane weighed 14 grams. I threw it 3 times, and it went 106 inches to 139 inches. The sixth paper airplane weighed 16 grams. I threw it 3 times, and it went 116 inches to 228 inches. The seventh paper airplane weighed 12 grams. I threw it 3 times, and it went 234 to 300 inches. Paper airplane number 7 wins. On this plane, weight was mostly in front. This is not what I predicted.
Project I did, fruit electricity. My question was, which fruit creates the strongest battery? Research and information that I found was when two different metals are placed in a common conducting solution, electricity will be produced. A wet cell battery consists of a negative electrode, positive electrode, and an electrolyte which conducts ions. In this case, the zinc is our negative electrode, copper is our positive electrode, and the citric acid in the fruits that we tested is our electrolyte solution. In this experiment, the zinc is more reactive than the copper. It loses its electrons more easily. Those electrons become zinc ions. The electrons flow from the zinc to the copper through a circuit. The multimeter was used to test the amount of electricity that was generated by the fruit cell battery. My hypothesis is that a lemon will conduct the most electricity and a banana will conduct the least. The materials I used: banana, an orange, lemon, a lime, a potato, a kiwi, a tomato, multimeter, alligator clips, zinc screw, and a copper penny. My procedure: I gathered my supplies, tested my multimeter with known battery voltages, softened the fruit, placed a thin slice in the fruit, and stuck a penny in it. Then I screwed a zinc screw into the fruit. Then I used alligator clips to connect it to the multimeter. Last, I recorded my measured volts. Fruit battery volts. Before we tested a multimeter with known battery voltages. We tested a 9-volt battery and a 1.5-volt battery. They were both accurate. It showed our tool worked. We built fruit batteries with 7 different fruits and measured the voltages. Results: the lemon had the most at 0.85 volts, and the lime at 0.82. The kiwi had 0.49 volts, tomato had the least at 0.39 volts, and a potato had 0.79 volts, orange had 0.71 volts, and a banana had 0.63 volts. In conclusion, the lemon created the strongest fruit battery, and the tomato was the weakest battery. As a bonus, we tried to connect the fruits together to light up a light bulb, but we could not build a strong enough battery. Something to figure out next time. Bye!
Okay. So, my topic is The Greater Explosion by Maeve. And yes, now let's begin. My question is, which will make the greater explosion? My research and information is search up what reacts with baking soda. So I did that, and there was a lot of things. But, well, you know. Okay. Next is my hypothesis was
My hypothesis is that vinegar will explode more with more baking soda. I think also that the 1/4 cup will just foam, no explosion. Okay. My materials I used was vinegar, Coke, baking soda, beakers or containers for experiment, and number 5, eye protection, which you can see in the video I accidentally forgot to do. I should have worn sunglasses. Okay. So for this one, vinegar, for number 1, vinegar, add 1.5 cup of baking soda. Number 2, Coke, add 1.5 cup of baking soda. Vinegar, add 1/4 cup. And same, Coke, add 1/4 cup. And next, so I'll go back to this one. I'll go back to this one because it's on the end of the slide, because I forgot why. Notes. Before, everything was ordinary. During, big films quickly came out. After, I noticed big bubbles sizzling on the 1.5 cup of baking soda. And so next, so this was the last slide. So you can see this was the vinegar test, experiment number 1. And we have the 1.5 cup, the 1/4 cup, and don't mind this in the back. I don't know why it's there. And those are the same, 1.5 cup, those other glasses. Okay, and I'll hurry up and play the video. Okay. Oh, this is the Coke. 1/2 and 1/4 cups of baking soda, and we have Coke, and Torrin's gonna be helping me, and we're gonna pour at the same time and see which one is the greater explosion. Okay.
It's okay. Just leave them.
Okay.
Okay, ready? Torrin, ready? Set, go.
See, mine went off the top, yeah, and I saw it went. It kind of looks like a tie, but the 1.5 cup did win. Well, yeah, because it did the same. With the Coke and the vinegar, they both, with the 1.5 cup, both went faster for some reason. Unless I got that wrong. But yeah. And oopsies. And so that is the greater explosion. That was my experiment, and it turns out the 1.5 cup had a faster reaction, which, if you don't know why, it's because the 1/4 cup, it has a little amount than the 1.5 cup. So the baking soda has a quicker reaction with the 1.5 cup, yeah. So then the 1/4 cup has to take longer to mix together. Yeah, that's why. And yeah, that's the greater explosion. Bye.
For my science fair project, I did a homemade lava lamp. So, okay, the slides might move a little bit, so that's why it might take a little bit long. Okay. So for my question, I did what different sizes are the little bubbles are. I want to see if they're bigger or smaller than inside a lava lamp you can buy. Then for research and information, once I put the Alka-Seltzer inside the bottle, it looked super cool because it made some bubbles. Okay, my hypothesis. I think what will happen is that the Alka-Seltzer will make bubbles. And for my materials, you will need one clean plastic soda bottle with cap, or you could use a water bottle. Then you need vegetable oil. Then you'll need one Alka-Seltzer tablet for a 16-ounce soda bottle, or 2 tablets for per liter bottle. Food coloring and water. For my procedure, gather materials over a surface that cannot be damaged by oil or can be wiped clean. Another good option is to cover a table with old newspapers. Fill the plastic bottle 3/4 full with vegetable oil. Add water to the neck of the bottle, leaving a little space between the water line and the top of the container. You can always add more water at a later time. Decide on a color for your lava lamp bottle. Select the food coloring accordingly. Add 10 or more drops of food coloring to the bottle until a rich color is seen. Break the Alka-Seltzer tablet into smaller pieces, 6 to 8. Add one piece at a time, observing each reaction. When the bubbling stops, replace the bottle cap. Tip the bottle back and forth and observe the reaction. Tip, twist, and shake the bottle in different directions. Observe the reactions and take notes. Okay, for my notes, I put the color that I put into the bottom was floating to the bottom of the bottle. It looked so cool. Once I put a piece of the Alka-Seltzer, it started making bubbles. The more Alka-Seltzer you put into the bottle, the more bubbles. After, you don't really see the bubbles anymore. Okay, my conclusion. After the bubbles go away, it kind of just sits. It also kind of looks like a drink or something. But there are still some bubbles after it sits for a while, but not as much as there is when you add more Alka-Seltzer. So yeah, that's my science fair project. Does the number of Mentos make the difference, or what kind of soda is my question? Then I researched about why Mentos make soda explode, and there's something called gas bubbles, and they want to get out like they're in prison. Mentos are bumpy, but we can't see it without a microscope. Because of that, Mentos dissolve carbon dioxide gas, which makes the water break easier. The speed at the Mentos fall through the soda affects the explosion. So the faster you drop the Mentos in the soda, the higher it would go. To make those bubbles, the carbon dioxide bonds with the water must be broken. Here's an example. The carbon dioxide is the cops, the bottle is the jail, and the soda is the criminal, and the Mentos are the getaway. Then my hypothesis is I think the Diet Coke in the big bottle would make the highest with 8 Mentos. So here's how I would do the process. Set down the camera, put down the soda in the front yard, open the soda and put Mentos in. Run away from the explosion like I was in war and it was a real bomb. See how high it is. Then redo until done. When we know what made the highest, we do it 4 times with 2, 4, 6, 8. So I made some charts and some videos so you can see the explosion. That only went like 1 foot. There's the Raptor explosion. Then this is Sprite. Big root beer. And yeah, 3 feet. Yeah. So the small root beer is 1, same as small Sprite and Diet Coke small. They're all 1. Then here's the difference, which only comes from the big bottles. Root beer's 3, Sprite is 4, and Diet Coke is 8. So so I told you about I'm gonna do it 4 times of whatever made the big explosion. So yeah, I'm doing 2 Mentos for this one. So the one that I did with Mentos is 6. The one that I did with 4 was 8. The one that I did with 6 was 9. The one that I did with 8 was 8. My conclusion was that I was half right. Diet Coke makes the highest, but I realized that the Diet Coke was with 6 made the highest. But the Diet I was half right. Diet Coke makes the highest, but the Diet Coke with 6 made the highest. I realized that it matters about the speed and how much Mentos. Also, it doesn't matter what kind of soda. No, it does matter what kind of soda. So I saw that at the beginning, Diet Coke was really different from the others. Then I saw that the faster I put in the Mentos and the soda, the faster and the higher it would go. Root beer was the least, Sprite was medium, and Diet Coke would make the biggest that I known. Well, I knew that it would make the biggest explosion. They all had different amount of soda at the end, but the one that I did with Diet Coke was really similar, and it was like super hard to which one's more, because they were all the same. It makes sense because they had the same kind of soda, and yeah, that's the end of my presentation.
My name is Owen Fewer. My experiment is called liquid density. My question was, do all liquids separate or mix together when added in a glass vase? Also, will solid objects sink or float in different liquids? My research and information was, a liquid like a solid has weight, called density. The density of a liquid is a measure of how heavy it is. When measuring 2 volumes of liquids, the heavier one is more dense. Less dense liquid will float on top of water, and more dense liquid will sink underwater. My hypothesis was, if I took a glass vase and put 9 different cups in it, then I will discover the density of each liquid, because they will separate and not mix together. Here is a list of all the materials, liquids, and solids you need for the experiment. My procedures were, gather all the materials and put half a cup of each equally liquid into 9 different cups. Don't forget to label the cups in order like this: honey, corn syrup, 100% maple syrup, whole milk, dish soap, water, vegetable oil,
rubbing alcohol, and red lamp oil. Next, use the blue food coloring in the rubbing alcohol, or else you can't tell the difference between the water and the rubbing alcohol. Then, while you are pouring the honey, corn syrup, and 100% maple syrup, you must carefully layer them into the vase, and don't let them touch the sides of the vase like I am doing in the top left picture. After the maple syrup, I use the turkey baster to pour the liquids in slowly. Then, starting with the water, I pour the rest down the sides and not in the middle. Here is what it looked like when all of the 9 layers were in the vase and they didn't mix together in the bottom right picture. After that, put all the solids in the order at the top, and you see how heavy they are and which liquid they were in. My data and observation were I had to do this experiment twice because I learned that water cannot mix with lamp oil. So we had to get red lamp oil. I also learned that if you have to pour it in near the liquids very deep in the glass vase, or else it would mix past the whole milk in with the dish soap. My notes were, at the beginning, I thought it would work fine. It didn't really. During my project, some of the liquids started to mix because of the way we poured them. On our second try, we learned a lot from the first, and things got a lot better. After we poured the liquids, we put the solids in. Some went to the same, and some went to the different ones. My conclusion were my experiment worked because if I didn't put them in the order I did them in, they would have mixed up and not separate because of the density of the different liquids. Thank you for reading it with me. Bye.
Hi, my name is Paisley, and my presentation is about cake. My question was, what will happen when you switch baking soda and baking powder in a cake? What I found was that baking soda and baking powder have a lot in common, but are different in the cake. Baking soda is a commercial name for sodium bicarbonate, and baking powder also has bicarbonate, but it also has powdered acid as well. I think that the cakes will cave in, and if so, the cake might taste different than normal, and maybe feel different and look different. My materials were baking supplies, which were in my kitchen, baking soda, baking powder, which were also in my kitchen, and cake recipes, and my brother to taste test. My procedure was I will bake the cakes, I will have my brother taste test, I will write down the differences, and I will see if my hypothesis is correct. My notes. Before, while I was mixing the cakes together, I realized that the baking soda batter was way more lumpy than the baking powder, and the baking soda batter was a tiny bit darker than the baking powder batter. While the cakes were baking, I realized that the baking powder turned more light than the than when it was in batter form, and the baking soda, on the other hand, was getting darker than batter form, and it was also getting smoother as it was cooking. After, when my brother was taste testing, he realized that the baking soda cake was dry and the baking powder cake was moist. The cakes were two different colors when they were done. The baking soda cake was darker, and the baking powder cake was light. And then, in conclusion, my hypothesis was kind of correct. The baking soda cake was much darker than the baking powder cake, and the baking soda cake was also more dry. So I would say don't use baking soda if you don't have to.
My science experiment was the glue challenge, so I'd be testing the strength of glues. My question was, which glue is going to be the strongest? My recent information said that the board's rope and the length of the rope and boards would need to be the same, and the order I put the weights in to test how much they could all hold. And it said that wood glue would be the strongest, but from different websites it said different things. Alright, so my hypothesis was I thought that wood glue would be the strongest because we're using wood. My materials, since I was using 6 glues and I needed 2 boards, I had 12 wood boards, super glue, construction glue, wood glue, glue stick, Elmer's glue, and weights. And then I would glue 2 pieces of wood together with the perimeter and the squiggly line of the glue, and then put a hook on the bottom of the 2 pieces of wood that I glued together, and then put the bucket on the hook, and then put weights in the bucket, and keep adding weights until the wood rips apart. My data and observations: when I was gluing, the glue stick was not holding. The hot glue might have dried before I could put it on, and Elmer's glue was having a hard time when I was squeezing it out. I was having a hard time getting glue out, but I think I got it. And then notes, for before, I put what I did on the last slide, and the bucket and the hook held 2 pounds, so I was going to need to keep track of that. And then during, so we had 2 contraptions. The first one, we realized that the glues held a lot more, and the bucket was just starting to droop down rather than the wood splitting apart. So, but we gotta test all of them to 75 pounds, and super glue held 140 pounds. And then day 2, with the second contraption, Elmer's glue held at least 230, but we had to stop because the experiment was no longer safe. And then after, final results were super glue to 140, and then Elmer's glue to 230, and then all the others glue held at least 75, but we didn't get to test them. And then conclusion: the hypothesis was not proved or disproved. All we knew is that super glue glue stick did not hold any weight, and the glues held a lot more than we anticipated. And then for fun, we just looked up the answers, and super glue could hold 10,000 pounds, construction glue could hold 4,000 pounds, wood glue could hold 3,600 pounds, glue stick held 0, we figured that out. Elmer's glue held 3,600 pounds, and glue gun held 600, 700 pounds. On the right, that's a picture of our contraption, and we just put weights in the bucket until the wood rips apart, and then did. And we had to make sure that the hook that we put in did not screw in all the way into the second piece of wood, and it didn't. And then on the left, we just put weights in the little box. And then I wrote about how we only got to test Elmer's glue and how all the others held. And then experiment in motion. On the far right, you can see that's how much glue I put on, with the squiggly line in the middle and a perimeter. And then on glue gun, my handwriting was too messy, so I just typed it out. All right, and then on the upper left corner, I guess, Elmer's glue was the only glue I got to test with the new contraption, and you can see I could actually sit in it and put bricks in it, and it still did not rip apart. But then our metal started to bend,
So like the hooks on the bottom holding it up started to bend this way, and the screws that were holding it up started to bend. And then right here on this one, I don't know if you can see, but the rubber on the hook started to come off, so we had to stop. And that was pretty much my science experiment.
For my science fair project, I did water filtration. And my question is, can dirty water be filtered? First, I was wondering how much of Earth's water can we actually drink? 72% of the Earth is covered in water, but 97% of that is salty water and not suitable for drinking. Fresh water is found in places like glaciers, lakes, ponds, rivers, and streams, and even from that 1.2% is drinking water. So can we clean water so that we can? If we use enough filters, we can clean it up pretty well. Not suitable for drinking, but the filters removed a lot of debris and yucky coloration. We used coffee filters, cotton balls, sand, activated carbon, small gravel, and large gravel to filter the water. After pouring really dirty water through the top of our filters, we saw it come out much cleaner. The filters caught the plant debris and the dirt we added to our water. It even absorbed the vegetable oil we added. In conclusion, the filters did a good job, but I wouldn't say it was drinkable.
This was my science fair project. My question was, will the height of the seat on the zipline affect the speed? And which seat is the fastest? Research and information. We found that the lower surface area of something affects drag. If you put more weight in the front of it, it might increase the speed because it gives more momentum to the front, which increases speed. We also found that some variables that could be the change the speed, like wind, zipline placement, and mass. My hypothesis was, I think the seat being at the top of the zipline / near the handle was going to be fastest. The materials I used were a stick, weights, Mom and I, stopwatch, and tape. My procedure was, first I would set the zipline to high position. I would count down 3, 2, 1. My mom would start the timer and I would release. It would stop when it hit the end point. We reset this and did this 10 times. When done, we set to low position. Then we did this entire process 10 times in low position. Here are some pictures of me holding the thing in high and low position. Before we got all set up and we did our research and headed to the platform and did a test run. It was good till it did not make, and it did not have enough mass. So we tried 10, not far enough, 20, not far enough, 30, just right. We tested for the high and low, but we lost when we were started, so we had to do it again. So we used tape, and then that got stuck in the zipline thing. That goes onto the wire. So we used a stick, and it worked. When we were done, we noticed the way I let go of the zipline affected the speed a little bit. In the end, we had our conclusion and knowing which would go faster, and had fun. In conclusion, it was sort of wrong. When the seat was lower to the ground, it went faster by milliseconds. But after I went on it, it was faster, so the weight highly affects the speed.
Hi, my name is Tyler, and my science fair project is what conducts electricity the best? My question is, what conducts electricity the best? So I have nail, copper, coin, pencil, water. Pencil lead is a bonus. Salt water, bonus for science. So all these. My research and information. Electricity is the flow of electrons and are the size of atoms. Voltage is a measure of the pressure that allows electrons to flow. Amperage is a measure of volts. Resistance is a measure of the opposition to current flow. Conductor is something that lets electrons flow. Examples are copper, steel, and aluminum. My hypothesis is I think that the nail will conduct electricity the best. My materials are battery, wire, my board I made with my father, my multimeter, which is this cool gadget, my test subjects, which are these, and that's it. My procedure was to build this circuit, control the voltage in amperage, complete the circuit using the different objects, measure voltage loss with this gold gadget, and measuring resistance, still using this. My notes are, nail conducts electricity. Let's see how bright the light is. So we can see that it's pretty bright. The resistance is 0.3 ohms. Voltage loss is 0.16 volts. Copper, which is this, conducts electricity very well. The light is very bright. Let's see how bright it is. That's pretty bright. Copper conducts electricity very well. The light is very bright. Voltage loss is 0.11 volts. Now, time for my quarter coin. The coin conducts electricity. The light is bright. Resistance is 0.2 ohms. Voltage loss is 0.29 volts. Aluminum, which we use this for, conducts electricity. The light is bright. Resistance is 0.2 ohms. Voltage loss is 0.23 volts. Now time for my pencil. Now let's see which one this is. This is an insulator. The pencil conducted no light. Resistance. This meter could not even read it. Voltage loss was no flow. Now, water is an insulator. There was no light. Resistance is 55,000 ohms. Voltage loss is no flow. Time for my pencil lead. Make sure that's off. It barely conducts light, but the light is dim. Resistance is 14.8 ohms. Voltage loss is 0.11 volts. Time for some salt water. Hey, that conducts electricity, but the light is kind of dim. But it actually is kind of medium, actually. Resistance is 2.6 ohms. Voltage loss is 0.13 volts. My conclusion was, copper was the best conductor because it produced the brightest light. It had the lowest resistance, 0.1 ohms. It had the least voltage drop, 0.01 volts. It drew the least amount of amps, 0.0. I found it interesting that this salt water conducts the electricity, but tap water does not. This must mean salt particles conducts electricity. And that's my science fair project.
Hi, Mrs. Bristol. Today I will be sharing with you my bubblegum experiment for my science experiment. Scientific questions. What brand of bubblegum will make the biggest bubble? Hypothesis. I think the double bubble will make the biggest bubble. I think this because it is the thickest of the brands. Hypothesis. Hypothesis. I think the double bubble will make the biggest bubble. I think this because it is the thickest of all of the brands. Materials. 5 different types of bubble gum, a ruler to measure the bubble, paper to record data, and a pen to write down the data. Procedures. Chew each brand of gum, measure the size of bubble, record size of bubble, Repeat steps 4 times. Compare the data to find out which brand makes the biggest bubble. Data and observation. The texture of the Hubba Bubba was very soft, and it fell apart very easy. After chewing it for a while, it made a pretty big bubble. The double bubble one was much harder than the Hubba Bubba and still made a good sized bubble. The Trident brand barely made a bubble. It was also a very small piece of gum. The Airheads gum was also a very small and barely made a bubble. The Bubble Yum was the thickest, chewiest piece of all and made the biggest bubble. Notes. Before, the brands of gum were all different sizes, thickness, and texture. During, some of the brands of gum were really soft and made it really hard to blow bubbles. After, my hypothesis was wrong. The Bubble Yum ended up being the biggest bubble, but the double bubble was right behind. Conclusion. I blew the biggest bubble with the Bubble Yum brand of gum.
My project is bath bombs by Veronica. My question is, does bath bombs work better without baking powder or without Epsom salt? Does a water bath bomb work better in cold water or warm water? My research and information is I did a lot of cool facts, like this one. Did you know each employee called compounders can make 700 bath bombs a day? I had no idea. Did you know there was actually a bath bomb named Blackberry? It was one of the very first bath bombs, and it's still produced today. Did you also know that bath bombs were invented to alternative or substitute for bubble baths for sensitive skin? I had no idea. Bath bombs were also made in 1985 and were invented by a person named Lush. Old bath bombs a good fact is old bath bombs will fizz more slowly than fresh ones. My hypothesis is I think that the bath bomb without baking powder would be worse because when I made it, it was very lumpy and it had hard to take out of the mold. I think that Epsom salt does not have to be added to a bath bomb. My materials are baking powder, citric acid, cornstarch, number 4, Epsom salt. This is optional. I didn't use it, but you could. It's a coloring pigment. Melted oil or vegetable oil, water. This is also optional. It's food coloring, or I used actually gel coloring. You can use mold for the bath bombs in a bowl. To get all your materials, all the steps I need: first, get all my materials. Second, make my bath bombs. Third, experiment them. Fourth, record my information. And fifth, I am done, I guess. My data and observations. The bath bomb without baking powder was not going as planned. It crumbled and it broke while I was trying to get out of the mold. My notes are before, when I was making it, bath bombs without baking powder were very lumpy, broke very easily, and were just very hard to take out of the mold. They just didn't want to come out. The bath bomb without Epsom salt was doing just fine. In fact, it came out of the mold very nicely, but the explosion was like 5% lower than the normal bath bomb. During this process, the one without baking powder almost didn't even explode. It exploded like 10 out of 100. It just laid on the bottom of the bowl. The one without Epsom salt exploded like 95 out of 100. It was really big. Nice.
I searched it up, and after that, I searched it up, and I saw that baking powder and citric acid made a chemical reaction for the bath bomb to explode. Quotation marks. After the one without the Epsom salt stayed in the bowl for like 2 minutes, it just acted normal. It just disappeared like a normal bath bomb. Nothing new. I came to a conclusion that if you don't add baking powder to your homemade bath bomb, do not be surprised if the bath bomb does not explode. And for no Epsom salt, you don't have to add it. But it does make your bath bomb look a little more fancy. About the hot and cold thing. So they seemed... It was really hard to tell them apart. They seemed almost the same. It was like telling twins apart. I kind of gave up, because it was really hard and you couldn't really tell the difference. So I came to a conclusion of that the water temperature does not really matter. My final conclusion is, if you don't add Epsom salt to your bath bomb, it's okay. But if you don't add baking powder to your homemade bath bomb, then it will come out not very good. Because as said already, the chemical reaction is only through the baking powder and citric acid. And if you want your bath bomb to look like a bath bomb, then you want it to look like a bath bomb, and explode, quotation marks again, then you should add baking powder. And if you don't add baking powder, your bath bomb will not work out as planned. So yeah, that's my project, and yeah.
Here's my science fair experiment. And so my question was, which paper towel brand is the strongest? And my research and information was, there have been experiments on which paper towel brand is the strongest. And the 3 strongest ones are Viva, Bounty, and Brawny. I have gotten 5 different paper towel brands, and we'll test which one will break the easiest to strongest when it's soaked by pulling it apart. And my hypothesis was, if I test which paper towel brand is the strongest, Bounty will be the strongest. And my materials I'm now needing is like the Bounty brand, Viva brand, Brawny brand, Value brand, and Snowsoft brand with a bowl and a hose. My procedure was to gather the materials, fill the bowl with water, get a paper towel soaking it up with water, pull it apart, record how easy it was to break, and to continue this with each paper towel brand. My notes were, before, I thought Bounty was going to be the strongest paper towel brand because of the way it's marketed, and they claim to be the strongest. And you'll find it on you'll find it on a commercial a lot. During the procedure, Snowsoft and Value were the easiest ones to rip, though Value was a little bit tougher than the Snowsoft brand. I did Bounty, then Brawny, and it seemed that Bounty was stronger than Brawny. Then I pulled apart Viva to see that it was stronger than Bounty. And after the experiment, Viva was the strongest one. In conclusion, I first thought that Bounty would be the strongest, considering that it's so popular. But Viva actually was. Meanwhile, Brawny was the 3rd most strongest, Value being the 4th most strongest, and the weakest brand was Snowsoft.
Alright, so this is my Jello project. Alright, so I wanted to know if Jello could be made with just warm water, or like room temperature water, instead of boiling water, then cold, or if I could make Jello with the regular process with soda instead of water. Alright, I learned doing my research that in Jello there's gelatin, sugar, artificial flavor, and artificial color. I also learned that gelatin is made of collagen, which is a protein found in animal bones, skin, and connective tissue. I also learned that the boiling water and the cold water are essential to making Jello. And my hypothesis was that if I use room temperature water instead of boiling hot water, then cold to make Jello, it will not turn out right. And I think if I use soda instead of water with the regular process, it will work. So my materials are I use 2 Jello packets. So how many you're gonna do, you can use as many Jello packets. You just need room temperature water, 2 bowls, a small pot, 1 measuring cup, 1 bottle of soda, and 1 stirring spoon. And my procedure is that, so first you need to pour the Jello mix in a bowl, then you need to add 2 cups of room temp water, and then stir, then put it in the fridge. And you don't have to wait overnight, but that's what I did. You could just wait a couple hours, that will still work, but I just waited overnight. And for the soda portion, I poured the Jello mix in the bowl, then added 1 cup of boiling soda, then stir into Jello. Then I added 1 cup of cold soda, then I stirred that into the Jello. Then we put that in the fridge, and again, you don't have to do overnight. You could just do a couple hours, but I did overnight as well. So for my notes before the experiment, when I got all of the stuff ready, after I got all the stuff ready, I decided to use blue Jello for my room temperature water experiment and orange Jello for the soda experiment. While I was doing my experiment, the room temperature one looked like it was working because, as you can see in the picture right here, it just looked like normal Jello liquid, what it looks like before you put it in the fridge. But for the soda one, when I poured the boiling soda into the Jello mix, it fizzed up and got some foam, like a layer of foam on the top of it. After the experiment, my hypothesis was correct, because for the room temperature one, it stayed the same liquid like on the last slide, and as you can see, it was still like liquid, and it had like slimy chunks of gelatin on the bottom of it, on the bottom of the bowl. So yeah, and then the soda one, it turned into Jello, as you could see right here. It looks like Jello, but it had a really good fizzy taste to it because of the carbonation in the soda, and it had some like bubbles on top, which was kind of weird, as you can see right there. Like on the top, there's like a little layer of bubbles, but it tasted really good. All right, so for my conclusion, my hypothesis was right. I learned you must have boiling liquid and cold liquid to make Jello. You need the boiling water because it dissolves the gelatin powder and breaks the protein strands apart. Then, when you add the cold water and refrigerate it, the protein strands reconnect and absorb the water to hold the gel together and make the wiggly jiggly stuff we love to eat. So, that is my science fair experiment. So, bye.
Test 1. Food. Right here is peanut butter, apple, and carrot.
This is Dash. We will be seeing which bowl he goes to. Go. Looks like he went to the peanut butter, carrot, and apple. Okay, now try to let Dash go and see which one he chooses. Peanut butter again. Test 3 food test. Since Dash went to the peanut butter, now I took out the peanut butter, and so all there is the carrot and an apple. And we're also going to see if Dash eats the apple because so far he just sniffs past it. So let's see. Did you gonna eat the apple? Apple? No? No? Okay. Looks like he doesn't like apples. Color test 2. Blue bowl is the farthest. Clear is in the middle, and the closest is the silver. Ready, Dash? Choose. Silver. Toy test 1. We're gonna see if Dash wants to play with 3 toys. Dash, choose toy. They're a little dirty because he brings them outside. You don't want to play with tiny toys? What? Ready? No? How about this toy? Fish, how about this toy? Looks like he prefers the shark toy. Toy test 2. Ready? How about this one? This time he likes the alien better.
My research topic is kind of like I'm trying to research if I can recreate an owl pellet and I've got to research how owl's stomach acid breaks down food, what is in the owl pellet, and most importantly, how to have fun. So my hypothesis is the owl swallows the food, and the owl swallows the food, and its body kind of breaks down the food, and the fur closes around the bones and makes an owl pellet. I don't know how to explain that very well, but my steps are I had to go get an owl pellet. I had to take it apart, which was kind of disgusting. I had to create something like the owl's stomach acid, which I actually just did warm water because I didn't exactly know what the owl's stomach acid was, and I was having a very hard time finding out. And then I had to do a bunch of research, and I have to now try to put the owl pellet together. The stuff that I have together is the fur from a shedding rabbits. I've got 2 of them, they're adorable. Some rodent bones, which I can find on Amazon. Warm water comes right out of my faucet. And rubber gloves, which are optional. And a clear cup so that you can kind of watch what happens. And yeah, that's about it. So I hope that you can kind of picture my experiment in your mind and
Okay, so my science experiment was off of rock candy. Rock candy by Arnaz. My question was, would rock candy taste different if I use different kinds of sugars? For research and information, I didn't do a lot of research or learn information, but the only thing that I could write down was that rock candy is usually made with granulated sugar, and it's literally just made with water and sugar. It's really easy to make. So I decided to make it at home. And my hypothesis was if I use different kinds of sugars, the candy would taste different and look different. The materials you need 10 different kinds of materials. You need, well, only if you're making multiple different kinds. You need granulated sugar, you need water. Those are the two basic ingredients you need if you want to make just one rock candy, but I decided to make multiple. So you need granulated sugar, water, caramel, brown sugar, a pot, some kind of stove, some kinds of clothespins, or I don't know, clips, right? Like these. You need a stove. You need a stove, you need some clothespins, you need something to stir your pot with, you need some sticks, and you need some jars or bowls. And the procedure, first you take your stick and dip it into water, and then you need to cover in whatever kind of sugar you're using. Then you put your pot on your stove and set it to high, and you put 1 cup of water in it. And then you need 3 cups of sugar. You need to put 1 in, mix it up a bit, put another in, mix it up a bit, put the last one in, and keep mixing it. When it starts bubbling and it's clear, that means it is ready. And then you gotta let your mixture cool and then pour it into your jar or cup. And take this clip, put it on your stick so your stick carries 1 inch from the bottom of your cup so the crystals can grow. So my notes were that this before, right when I put the sticks in, honestly, no candy was growing because it doesn't happen in a snap. Life doesn't happen in this. Well, life probably does happen in a snap, but this doesn't happen in a snap. The cup smelled really good because of the syrup, especially the caramel one. It smelled like caramel. The whole house smelled like caramel. And then during every day, you could see the crystals grow bigger and bigger, get more stuck to the cups. The top of the cups where the bit of the syrup was, if you touched it, which I wouldn't recommend doing because you don't want to disturb your candy, but if you touch it, it would be hard, I guess this desk. It wouldn't move like syrup would. And after, the cup still smelled great for some reason. There are crystals all over the cups, but there was crystals all over the cups and sticks, but on the caramels, there were no crystals. It just looks like a layer of caramel on it. And my conclusion is rock candy can only be made with brown sugar and white sugar. And then here's a picture of my rock candy. This one is the brown sugar one, the one with the purple clip. And I think the middle one is the one that was just covered in water and then put in caramel and then just had to grow. And the one on the right is the one that was dipped in water, covered in sugar, and then put in the caramel one. And now I will show what my brother thinks of this. Okay, so what do you think of the rock candies?
I like this one the best, the brown sugar one. That's because, both of the caramel ones,
they turned out to be paper. So the caramel kind of got stuck to the paper part of the stick. So when you were biting into the caramel, it kind of smelled and tasted like caramel, but it's actually paper. So I do not recommend making ones with caramel. No, goodbye. And this one is great. It honestly tastes like a normal rock candy, but just brown sugar with water.
And better.
Yeah, and better. And the white sugar one got stuck in its cup, so I wasn't able to bring it. But this is what it looked like from the inside. It looked really cool. But it's gonna be a problem how to wash it out. But yeah, those are the rock candies.
I really wanted to eat
what
that
you learned
one.
from this: never make rock candy with caramel. Thank you for watching.
I wanted to eat
this.
the stuck one.
Goodbye.
For my science fair project, I did the human heart rate. My question was, how will a person's heart rate change when put under different circumstances, such as riding a horse, playing guitar, and doing yoga? How could I prove this? From my research and information, I found out that the human heart rate is very complex and complicated. Your pulse or heart rate changes when you sleep, run, or even just by sitting down, really. Depending on how fast your blood is pumping, your heart rate will change. It can go fast after running or slow when you're relaxed and calm. My hypothesis was that my sister's heart rate would change when put under different circumstances, and it did, but the results were not what I expected. Some of the materials I used was a horse, a guitar, a yoga mat, a pencil, and paper. The procedure I did was I got my supplies. I did experiment 1, 2, and 3, and then I made a flip grid and completed the cycle. I'm making the flip grid. Some notes I took that was before getting on the horse. My sister's set heartbeat was 97 beats a minute, which was pretty normal. While she was on the horse, it was 109 beats a minute, which was a little high. And when she got off, her heart rate dropped back down to 98 beats a minute, so it became normal again, which proves my hypothesis that her heart rate went up when she was on the horse. While playing the guitar, it was 80 beats a minute, or before playing the guitar, it was 80 beats a minute. While she was playing the guitar, it was 100 beats a minute, and when she stopped playing the guitar, it was 93 beats per minute, which proved me wrong because I thought her heart rate would go down instead of up when playing the guitar because I thought it would be calm and relaxing. Before doing yoga, my heart rate was 109 beats a minute because my sister didn't want to do the yoga part. When I was in a pose, my heart rate was 150 beats a minute, so it changed by 49 beats. And when I finished doing yoga, my heart rate dropped back down to 109 beats a minute, which proves my hypothesis that my heart rate went up when doing yoga versus going down or staying the same. Here's some of the photos I got. Here's me doing yoga. This is my sister playing the guitar, and this is me taking my sister's blood pressure with the horse. That was my sister riding the horse. That was also me doing yoga. That is another picture of me taking her blood pressure while she was playing the guitar. In conclusion, I learned a lot. I learned that your heart rate can change just by doing the simplest things, like how her heart rate went up by 20 beats, and I thought it would have gone down or stayed the same. Overall, my experiment was really fun, and I also learned that when you seem calm or relaxed, your heart rate could be going crazy, which is really fun to think about because you could be sitting on your bed and your heart rate could be at 109 beats per minute, or you could be running and it could be at 150 beats a minute, which is crazy to think about just for a kid, or to see that something can pump that fast in just a minute. Thank you for watching my science fair project. I hope you have a great day.
By us in Jello. My question: how does the temperature of water affect the brightness of glow sticks? Research information. Wikipedia gave me stuff about what's inside of a glow stick. The base catalyst, the dipolyl L oxide, create the chemiluminescence, which is not the chemiluminescence does not create a similar, just gigantic amounts of heat. Hypothesis: if I put a glow stick in room temperature water, it will stay the same brightness. If I put the glow stick in hot water, it will glow less, and when it's in cold water, it will glow brighter. Materials: 1 cup of room temperature water, 1 cup of hot water, 1 cup of cold water, thermometer, and 3 ounces glow sticks, pretty much. Produce: I filled the water. I filled 3 glasses of water, then check the water temperature, put closed water at 5:54 p.m., wait and serve, pull out, glow sticks, take 10, pretty much. Observation, blah blah. Notes. No, first we did 3 cups of hot water and put them in room. We filled 3 cups, one with hot, cold, and room temperature. And then when we looked at them during our experiments, their color had been the same. And right here is when we pulled them out. Here, the hot water is that one, 155 degrees room temperature. That one, 67 degrees. Cold water, 48 degrees. Glow sticks place at water at 5:54 p.m. Picture taken 5:46 p.m. And then this is when we did around 6 o'clock. The brightness of a glow stick on the left is less bright than it was at 4:56 p.m. This is hot, this is room, and that's cold. Conclusion: my experiment disproved my hypothesis. When room temperature is somewhat stayed the same, but the cold water dimmed it and the hot water brightened
it. Oh, sorry. It's Liam Stevens right here, not Liam Stevens. Today our project is on a solar oven.
They mostly are the questions are, what is a solar oven, or how does a solar oven work, or how long does the food take to get heated in the solar oven? Those are all good questions, but we will be answering all those questions on today. Information and research. I said it backwards. The solar oven is made for outdoor and made from the radiation the sun gives off to heat the food, and that's why it's called a solar oven. And it releases gases and stuff. My hypothesis is when I put food or any s'mores or anything inside the solar oven, it will heat it very hotly, and it will cook like whatever I put in there, like a hot dog. My materials is cardboard, aluminum foil, plastic wrap, tape, and scissors with adult supervision. I forgot to put adult. I used the shoebox from my little sister's room, and I cut a big hole on top of it because we need a bigger hole. And I put plastic wrap over that hole and taped it around. And in the inside, I put many layers of aluminum foil and put a big one to break down to have more shine so it can heat up. My conclusion? The solar oven, when I heated it up, left it out there for 30 minutes. It was warm to the touch, it was hot, it was burning, it was steaming in the box. It was so hot. So I left it out there for like 10 minutes, and then I came back. I came back and took out the waffle I placed in there because who doesn't like waffles? I took it out, I placed it on the plate, and I put some syrup on it. It tasted not so good because it tasted like aluminum foil. My conclusion is a solar oven. Okay. How do I put in my own words? A solar oven is an oven used from solar radiation the sun gives off, like when it's heating up, and it can only this oven can only be used on hot days, not cold days. So it uses from the sun's solar radiation to heat up whatever inside. And these are my pictures. And a demonstration of how the solar oven works is the sun comes down and it reflects it, like these are the aluminum foil. It reflects off each one and it shines down here to whatever food or like waffle or s'mores is in there. And that's my conclusion on the solar oven. Last time my last take took a little too long, and also I couldn't finish, and I was making so many jokes it was cringy. These are many of my pictures. The tape of the hole, and the thermometer who was placed inside the aluminum foil. You see the big sheet inside. And my little sister's shoebox, I tragically cut up and she hit me. This is the Eggo I placed in here, and it didn't taste that good, but it was okay for first time solo.
Hello, my name is Xander Reed, and my scientific question is which battery lasts the longest? So let's go together and see which one actually does. These are my research on all the batteries I'm going to be using. Dursa Optimum is an alkaline battery and is also a AA battery too I'm going to be using. The package says that's extra life, X per hour. It costs $12.99 for a pack of 12 batteries. For Energizer Max, it's also alkaline batteries. It's also a AA battery I'm going to be using too. It's also advertised that it will just keep going and going and going. It says that's the world's #1 longest lasting battery too. Well, let's check if that's actually reasonable after this scientific after this presentation. It costs $9.49 for a pack of 10, and for Kirkland Signature, it's also an alkaline AA battery. It costs $16.99 for a pack of 48. Fun fact, it was also made by the Duracell company. My hypothesis is that if I put 3 different brands of batteries in the 3 separate but the same toy, then I think a Duracell will be the longest because, well, of all of its advertising. I think I'm persuaded now. My procedure is that I'll buy 3 different brands of batteries. I'll buy 3 of the exact same toy, put the batteries in the toy, start the toys at the same time, and the toy that lasts the longest is also the battery that lasts the longest. My materials is 3 different types of batteries, Arctic penguin slides, and a clock. My notes also say that, well, the notes I made is that I'll check in every hour to see how it's going. I'll not turn the music on because it'll drain more of the battery and it won't be accurate. Also, the batteries are working fine after an hour of battery usage, and at 11 hours and 42 minutes, Kirkland Signature starts to slow down. These are the times I started and turned the penguins off. I'm not going to read all of this. You can pause it to see when I did turn it on and off, but I'm going to go to the next slide because I'm not going to read all of this. These are some of the pictures of the materials I used. And now we are finally at the winners. And the winners are, in 3rd place, Kirkland Signature with 25 hours and 59 minutes. In 2nd place, Energizer Max with 34 hours and 37 minutes. And in 1st place, Duracell Optimum with 35 hours and 19 minutes. That's actually, Energizer and Duracell are actually a 42-minute difference, not really big difference. And in conclusion, it looks like the advertising for Duracell is actually right. It is the longest lasting battery, and my hypothesis was correct too. This was a very fun experiment, and maybe I should try which paper towel brand is the strongest next. But for now, my scientific question is now answered. Looks like Duracell is the longest lasting battery. So I hope you liked that, and now it helped you which battery brand lasts the longest. Bye.
This is my slide presentation. The question I asked was, what did the kitten or cat do? What will the kitten or cat do when going through the obstacles? Will he or she crouch down the narrow spaces and walk normal and ride ones? Well, where I got my research, my information is I looked at education.com for information on how cats' whiskers are, how important cats' whiskers are. And then my hypothesis is what I thought would happen is that the kitten will crouch down in tight spaces and walk tall and open ones. And then my materials I used was Storm or Kitten, boxes, a book for the triangle, our iPad to record it, and then tape and scissors to cut and glue it, cut and tape it. And then my procedure was I designed a course, my obstacles on paper. I found some boxes that could work, and then I cut and taped them together to make a obstacle course with wide triangle parts and narrow areas. I made sure she couldn't get out of open areas, and then I watched her do the course. And then some of my notes were that we taped them together and cut out some areas so she could walk through, and so she couldn't get out of one area. And then we also set up a book as a triangle to see if she'd go through it. And then during it, she was slow and looking around to see if there was another choice instead of going through the triangle book. And finally, when she did it, it looked like she crouched down at least a little bit, and she stayed in the tunnel for a while, and then finally walked through the book and went into the box, which we videoed. And then we picked her up, praised her for doing it, and then we watched the video we made. And then in my conclusion, Storm went through the maze and did what we thought she would. She crouched in a narrower space and stood up straighter in a wider one. She took way longer than I expected, though, because she was looking around deciding if it was a good idea or not to go through the triangle book.
Okay, go ahead. Close the door behind her. Don't push. Yeah, she made it through.
Oh my gosh,
forever.
Okay, so this is my floating orange project. My question was, if I peel an orange, will it float? And then my research and information was, is there air between the peel and the fruit? Is fruit more dense than water? Does an unpeeled fruit float? And how much water do I need? And then my hypothesis was, if I peel an orange, it will float in a cup of water. The materials are 2 oranges, 2 clear tall glasses, and water. And then my procedure was gather materials, peel 1 orange, put orange in water, see if it floats or not, and then record results. And then those were my pictures. This is the orange that was floating, and this was the one that was sinking. My notes were, before the glasses are filled with water, 1 orange is peeled. During, orange quickly sank to the bottom of the cup. After, the water smelled like orange juice. Also, the orange soaked up a lot of water. And then, conclusion, the peeled orange sank, which was surprising since it is lighter than the unpeeled orange. In conclusion, the peel acts like a flotation, which keeps the orange afloat. And then,
For my science fair project, I did a density rainbow. My question originally was, what would work better, honey or dish soap? The research and information that helped this was that what is a density rainbow is usually lighter and heavier liquids poured onto each other to form a kind of column stack, and it's called a rainbow because usually it has the colors of a rainbow when you stack them together. The materials I'm
I used for this project were honey, juice syrup, 99% alcohol, I wrote it as 90% for some reason, maple syrup, baby oil, and glass cups. We also used vegetable oil, but I didn't note that down. My hypothesis was honey will work better than dish soap. The procedure was to get their materials, note down as we do the procedure, wait an hour longer to make sure all the stuff settles once we do it, take pictures and videos, finish slideshow, and make the video. Before we had done the project, I thought that honey was going to work better and it would probably go on top of the stack or in the middle, because I had built like a plan thing where I would do heavy, light, heavy, light. But, it kind of meshed together. During the procedure, I still thought that honey was better because maple syrup and honey hadn't mixed yet, and the Dawn dish soap didn't have as much stuff in it in the glass. And I was positive that honey was going to work better. After the procedure, the dish soap definitely worked better than the honey, since the honey kind of combined with this maple syrup, which didn't really help at all, and it kind of, just turned into one. Yeah. The reason why was the dish soap didn't blend in with any other chemicals. In conclusion, I had learned that dish soap worked better than the honey in the density rainbows. No. For my science fair project, I had done a density rainbow. My question before I did the project was, what would work better, honey or dish soap? Basically, density rainbows are lighter, heavier liquids poured onto each other, and usually they're used in a certain way so the colors form a rainbow. It's kind of like a column stack. The materials I was using for this project were honey, dish soap, 99% alcohol, maple syrup, baby oil, and glass cups. My hypothesis was honey will work better than dish soap. The procedure was get materials, note down as we did the procedure with the column stacking, wait an hour longer for the stuff to settle in, take pictures and videos of the thing, finish my slideshow, and make the video. Before I had started the thing, I thought that honey was definitely going to work better since it was a denser liquid. During the procedure, I still thought that the honey one looks better, and the Dawn dish soap was kind of lighter, so it didn't really look that good, and we used less of it than we used for honey. And I was positive that the dish soap wasn't going to work as good as the honey did. And at the end, I had realized that the maple syrup and the honey had started to kind of mix to become one like whole brown liquid, so that kind of made it look a little not good, and it ended up turning out that dish soap is definitely better for a density rainbow, especially if you're going to use maple syrup too, or any other brown liquid. Oh shoot. In conclusion, I learned that dish soap worked better than honey in the rainbow density, and here's the pictures.
A Solar Power Oven by Zoe Rosinski. My question is, on a hot day with my solar power oven, the marshmallows will melt in the sun. My research and information. I looked up science fair projects on my link. Then I found something that looked interesting and easy, with stuff I had around the house. The marshmallows will soften or melt from the heat reflected from the sun off the tinfoil. My materials are a cardboard box, tinfoil, plastic wrap, scissors, and a stapler. My procedure is, I cut a box to make it have a lid that stands up. Then I placed it all in tinfoil. I placed marshmallows inside and put plastic wrap over the opening. Now I need to wait for a sunny day to see if the marshmallows will melt. I won't be able to observe until a hot day. But that's my picture of my solar power oven. My notes are, before, I love to bake and I saw crayons melted on our sidewalk, and I thought about a solar powered oven. The materials were easy to put together, and the plastic wrap might keep the marshmallows from drying out. After, I haven't been able to test it because we are waiting for a sunny day. I think that we will put it on our driveway, and my driveway is black. It will attract the sun and be hotter. My conclusion. A box wrapped in tinfoil traps heat from the sun, which causes the marshmallow to heat. And that is the end of my final science fair presentation.
Tasting Colors by Riley Harrison. Does the color of a food or drink affect the taste? Research and information. Scientists say that the color does affect the taste. They say that the color red makes the food or drink stronger. Hypothesis. My guess is that if you add food coloring to a food or drink, it will taste stronger. Materials. Food coloring. 2 to 4 drinks. Mine were water and ice. Cups and bowls. 2 to 4 foods. Mine were yogurt and sour cream. And 2 people. Procedure. Get 2 to 4 drinks and 2 to 4 foods. Then you make the food and drinks. Put the food coloring in half for the food and drinks, and the other half stays the same. Have 2 people try the food with and without food coloring. Notes. Before the experiment, they all tasted like the same old food and drink they are. During the experiment, we mixed the colors. After the experiment, we tasted the foods and drinks, and we found out that whatever the color of it, the food or drink looked like, that's what it tasted like. For example, I did blue, and I thought of blue raspberry, and that's what it tasted like. In conclusion, my hypothesis was wrong because the food or drink didn't taste stronger. It tasted like a type of food. Like if the coloring of a food was purple, it tasted like grape. It didn't taste stronger. And my friend Brooklyn helped me, and this is her. So I did, what did I do? Oh, I did red and yellow. So for the red one, I thought of either like cherry or strawberry, and that's what it was like a hint of it. Then I did yellow, and I couldn't really think of anything yellow, but there's like pineapple, banana, lemons, but I didn't really think of any of that because it didn't look like a bright yellow. So it kind of tasted like normal water, but yeah.
I did types of Oobleck. My question was, can you make Oobleck with something else besides cornstarch, like other starches and whatnot? My research and information was, Oobleck is interesting. It can go from a liquid to a solid. When you play with it slowly, it is a liquid that will run through your fingers. When you ball it up fast or punch it, it will become a solid. Nothing I used made a better Oobleck than regular cornstarch. My hypothesis was, can you make Oobleck with other powders besides cornstarch? My materials were cornstarch, baking soda, baby powder, flour, food coloring, water, glass bowl, and a speaker. My procedure, I can't say it, but was make a traditional Oobleck with 2 cups of cornstarch, 1 cup of water, and food coloring, just for fun. I did the same exact thing for all the other starches. My data and observations was the traditional Oobleck made a great Oobleck. Goes from solid to liquid as it is supposed to fun to play with. Baby powder, this Oobleck was hard. It would go into a liquid form, but hard to play with. It was not as much fun. Notes. Before, when I was making the normal Oobleck, I added 2 cups of cornstarch and 1 cup of water. So I did the same for all the others. During the
the one with flour and the one with baking soda did not work. Flour made a dough, baking soda fizzed a little and made a soupy mess. After, the best oobleck was the traditional plain cornstarch oobleck. Conclusion. So my hypothesis was not right. You can not make oobleck from other powders. You need cornstarch. Baby powder did not work, but the main ingredient in baby powder was cornstarch. Baby powder still did not work as well. It was hard. So that's about quite a bit of the thing.
Hi, so I'm going to talk about my science fair project, Rainbow in a Jar by Bailey Sargent. Okay, so my question is, what is the density of different liquids in a jar? And now here's my hypothesis. How does the density of liquids affect what it does in water? And then here is what I researched. Each liquid has different thicknesses and density. The heavier liquids will sink while the lighter ones will float. Here are the materials I used. Tall glass jar, food coloring, blue, red, blue, and green. Honey, blue dish soap, water, olive oil, rubbing alcohol, jars for mixing and pouring, and teaspoons for mixing. Here are the steps I took. So, the first step, add 1 red drop of food coloring and 1 drop of blue coloring and 1/4 cup of honey. Stir, mix. This creates purple color liquid. Pour the purple liquid carefully into the jar. So here is the purple. So as you can see, we did 2 drops of blue and 4 drops of red because the red was kind of light. And we did 1/4 cup of honey. For the second step, next add about 1/4 cup of blue dish soap to the tall glass jar. So this is what we did. And for the third step, add a few drops of green food coloring to 1/4 cup of water, mix until combined, then carefully pour the green liquid into the tall jar. When pouring the green liquid, tilt the jar so the liquid runs down the side of the jar slowly. Here is the green. So you can kind of see it bubbles up. Once you add the other liquids, it kind of calms down a little bit. And then for the fourth step, wait a few minutes and then pour 1/4 cup of olive oil into the jar. Again, be very careful when pouring in the liquid. Make sure to tilt the jar and pour very slowly so the colors don't mix. So here is what we did for the olive. And as you can see, they're starting to form a rainbow. And then for step 5, add a few drops of red food coloring
to 1/4 cup of rubbing alcohol and mix until combined. Then carefully pour the red liquid into the tall glass jar. Tip: I can't tell enough how important it is to tilt the jar, otherwise the colors will mix together and you won't get a and you won't get a full rainbow. So here's the red. So we use the alcohol, rubbing alcohol, and the food dye, and you can see it kind of combined all together. So here is the full product. You can see some of the colors. The blue and purple you can't really see because they're darker colors. So. Data and observation. In order for the colors not to mix together, we had to tilt the jar and pour the liquids in slowly. The liquids were odorless except for the rubbing alcohol. Notes. Before, I thought the liquids would mix together. During the experiment, we saw the liquids separate. And then after this experiment, it made a perfect rainbow in a jar. Here's my conclusion. Liquids have different densities. It was fun to watch the colors form a rainbow in a jar. And that's my science project.
So, the science project I decided to do is which paper towel brand is best. My question is which paper towel brand is better out of Bounty, Scott, and Brawny? The research and information I have was, according to Insider.com, they poured water on the paper towel, and I think Bounty won. My hypothesis is that Bounty and Scott will be better because Bounty is the quicker picker-upper and Scott because it might be thicker. Materials: 3 paper towel brands, water, a hard surface, 1/4 of a cup, and my procedure is, so you have to get 3 paper towels, you have to get the 1/4 cup water, then you pour the water on the table and you slide the paper towel across, and then you do that 3 more times for each paper towel. Then this is the water, and my notes are, I was going to pour the water on the table and I was going to wipe it down once and see how much it got. Then during the Bounty soaked up and got some of it. Then the Brawny and Sparkle did the same thing as the Bounty soaked up, then pushed the water. And after the whole thing, the one who won was, I think, Bounty won. It was hard to tell because the water was deeper and thinner, and it was in more space on the table, so it was hard to tell, but I think Bounty won. And then my conclusion is, I think Bounty won. I really did not know who was going to win, but I think Bounty did. It was hard to tell, but I would pick Bounty, I guess. Bounty is the pick.
In this experiment, we were testing rather water and oil mixed together through the lava lamp experiment. Oil and water, they do not mix because they can't form any chemical bonds with each other. Water is made of highly charged hydrophobic compounds, while oil is made of long chains of carbon that are hydrophobic.
We tested hypothesis. We tested to see if vegetable oil and water to see if they would mix. Vegetable oil, the materials we needed were vegetable oil, water, Alka-Seltzer, and food dye. First, fill 3/4 with vegetable oil. Then fill the rest with water and add the food dye, 10 drops. Then add the Alka-Seltzer. Some of the notes I took was when we started, we got all the materials we needed. Then we went outside, got some newspaper so we wouldn't make a mess. First, we put in 3/4 of vegetable oil. Then we filled the rest up with water. Put the food dye in 10 drops, and finally put the Alka-Seltzer in. When you put the Alka-Seltzer in, it made weird bubbles that float to the top. When the Alka-Seltzer stops, it shakes up. Shake it up real. I shaked it up real good, and it had a weird reaction. The bubbles went to the top, and it made their way down. My conclusion the lava lamp.
Everybody, my name is Brianna Lewis, and we will be finding out today clay shapes, which one floats. For my research and information, I looked up what is most likely to float out of clay shapes to give me a better idea of what I was doing and to find in the future. And what I found was displacement. Now I have a better idea for what my shapes and what I'm going to do in the future. In my hypothesis, does the shapes of an object made out of clay have anything to do with whether it will sink or float? And these are my shapes: a sphere, a boat or bowl, a cube, and a triangle. And for my materials, you need water, clay, a bucket or container. In my procedure, first I made the shapes out of clay. I filled the bucket or container with water. I put the shapes in the water. I recorded if it sinked or floated. Then I see if there was a pattern in the shape sinking or floating, and then if I could differ my hypothesis. And for my data and observations, I found out that the shapes had to be the same mass, or it would mess up my hypothesis completely. But lucky for me, these little blocks they were cut up into fourths, so I didn't have to weigh my shapes. And now it's time to test. But what I thought was the sphere and the cube would sink. But to my finding out, the triangle sunk as well, because I thought the triangle and boat/bowl would float. And I thought it was because of the density. And for my conclusion, I learned that this didn't necessarily have to do with the shape, but it kind of did, because if you had one shape that was completely different from the other, yes, it could have an impact on it sinking or floating. But if they're kind of the same shape, it won't have an impact because it's really close to the same shape. But the density really matters, I have a feeling, because the triangle was very, very dense. But the bowl/boat, it wasn't dense because it didn't have anything at the top of it. And that's what was my observation. Bye.
Mentos. Other reactions. Question: do Mentos react to other things than Coke? For a second there I thought it said cake. That would have been funny. Research and information. I found from Google that the reaction is a physical reaction, not a chemical reaction. The carbon dioxide gas in the Coke reacts to the Mentos, resulting in boom boom.
The Pepsi will boom, not as much as Coke, and Sprite will boom a little bit. Materials: 20 Mentos. There was actually 28, but we didn't use 8 of them. 3 Sprite, 3 Pepsi, 3 Coke for reference, and 2 Currents, 1 Gatorade. We used the Gatorade bottle so the volume would stay the same for each drink. And 1 bin for excess liquids. Procedure: fill Gatorade bottle with drink. Add Mentos. Quickly screw on cap. And you shake it. Take off cap and see reaction. And then repeat with the next drink until I'm out of drinks. The Pepsi actually did like the same boom as the Coke. Maybe more actually. And the Sprite barely did anything. The Kerns had a lot of small bubbles and foo sounds. Not really much other than that though. The Gatorade had bigger bubbles and it still had sound. Same sound, not bigger sound. Afterwards, I put all the cans and stuff into the recycle, and the excess bin, actually when I'm recording this, hasn't been dealt with yet, so I just put was dealt with later.
My name is Avery McHenry, and I will be testing how the different amounts of hydrogen peroxide affect the reaction of elephant toothpaste. We have 3%, which is 3% hydrogen peroxide. We have 6%, which is 6% hydrogen peroxide. And we have 12%, which is 12% hydrogen peroxide. And then here we have the yeast, and when you pour it in, you will get a reaction like this, and it will foam up. It will be kind of slow, but this is 3%, and now we're going to do the 6% hydrogen peroxide, and then the 12% here. Now you can watch as how they foam up and explode over the bottle. Now, as you can tell, over time the 12% will produce more foam because it has more hydrogen peroxide. And hydrogen peroxide is one of the most important things for elephant toothpaste. Yeast and water is what you need to make the reaction happen.
This is my science project. It is about strawberries. Molding strawberries specifically. My hypothesis is that the strawberry in the water and the one out in the open will mold the most, and the one in the container, the fridge, will mold the least. My experiment is that I will take 4 strawberries and put each in a different place. One in a sealed container, one out in the open or underwater, and one last one in the fridge. Leave them alone and take a picture every day for a week. This is the one out in the open. As you can see, on day 1, it was normal. On day 2, it was slightly wrinkling. On day 3, it was getting some white molds. On day 4, it was slathered in cream cheese molds. And day 5 was just disgusting. And, yeah. The one in the water actually created its own bubble raft and molded the most. Yeah, it was. But the cold one actually didn't mold at all. It was actually edible. But the one in the container was also edible. It tasted really weird. In conclusion, the one in the cold didn't mold, as you can see. The normal one became completely black by the end, and the one in the water was just disgusting.
Chicken Egg Project by Olivia Cipla. Does the chicken have the same colored eggs as their feathers? I chose 4 different chickens, each with different colored feathers. I then examined each chicken and made lots of notes of their feather, color, size, and the size of the chicken and the breed. My hypothesis is the chicken color of the egg is not related to the color of the chicken. Materials that you need would be 1 brown silky fancy chicken, 1 white silky chicken, 1 buff Polish chicken, 1 Americana chicken, 1 cage, 1 egg from each chicken, 1 notepad and pencil. I chose a chicken and picked them up and put them in the cage. Then I made observation notes on the chicken and waited for the chicken to lay the egg, and then I would remove the chicken and the egg and make another observation. Then I made a very detailed observation of the egg's color, size, shape, and the chicken's color, size, and shape. And then repeat those steps for each chicken. Oops, wrong side. There were so many colors of the eggs when you took them out of the nesting box: white, green, brown, all these colors. So many. But there's a variety of the chickens, so it makes plenty of sense. I decided to pull away 4 chickens to try the experiment. There was a light green egg by the Americana, and that was from the Americana, obviously. The white brownie chicken. Both the brown silkies laid the same color egg. And the Polish had a creamy, beautiful tan. It was really small.
like an inch. Chickens don't match the color of the egg, but the size of the color does not influence on the egg size. And here it comes to the conclusion. But now it is time for the truth. None of the chickens did not influence with the egg color, but it did influence with the size, as the Polish chicken with its yellow, white feathers. And the chickens did not lay the color of the eggs that it basically did, but like the silky still laid the same color eggs as the brown one. And that's where you can say no, they aren't the same color. So, but the feathers don't influence at all. I hope you enjoyed my bye.
My experiment is to test different materials for their ability to blow up a balloon. I will test dry ice, regular ice, and 7-Up to see which one blows up the balloons faster. Will any type of ice blow up a balloon? Research and information. Number 1, dry ice is made of CO2. Number 2, dry ice bubbles in water and disappears faster in water. Number 3, 7-Up has CO2 in it. Number 4, balloons will be used to measure the CO2 released from each bottle. Number 5, regular ice has little or no CO2, and so it should not blow up the balloon. My guess is that the CO2 in dry ice and in 7-Up is the reason for the balloons blowing up. If this is true, regular ice will not blow up the balloon because it has no CO2. I'm also guessing that making dry ice melt faster will blow up the balloon faster. Materials needed: 4 plastic water bottles, crushed dry ice, crushed regular ice, 7-Up, and balloons.
What we got here is the balloon blowing up on the water bottle. We got 4 bottles. One has dry ice with water, with no water in it, and it's trying to blow up the balloon. And one has water and dry ice in it, and it's blowing up the balloon like crazy.
In fact, it got ahead of us before we started filming. It was already blowing up, and it's still growing.
Oh my gosh.
Is this? Go ahead.
And then number 3 is just ice, not really doing much.
Wet ice, regular
ice. And then for number 4 is carbonated water, which is deflated like the regular ice.
Well, shake it a little bit and see what happens. Shake it up a little bit. Okay, so that helps. Okay.
And now it starts blowing up.
Okay, so you see you released some CO2, didn't you? And now it's blowing up. So our regular dry ice, is this what you expected?
No, I thought it would blow up a bit more, but yeah, I thought it would be like that too because there's no water making it blow up and like air fuming out, and so it would stay like that. And this, the water makes it go kaboom, and then it makes the air go and makes the balloon go.
So it really is about the fact that dry ice is surrounded by a very relatively hot water.
Yeah.
But the dry ice is surrounded by air. It's not as much molecules touching it, right?
Yeah.
Not as much molecules melting, evaporating the dry ice. So it's kind of it goes exactly with what you expected, right?
And
I hear it hissing. One of the balloons is leaking.
No.
Well, this balloon's about to pop, so we're going to stop the video. Interesting experiments.
Yeah.
You'll discuss it, right?
Uh-huh.
Okay, very good.
Because the water bottle openings were small, I had to crush up dry ice and put into the bottles. I also hurried to get everything ready to go because I knew this would be a fast experiment and things would move quickly. I had my experiment drawing in front of me so I could see how to set the stuff up. As I expected, the experiment moved very quickly. We took a video of our experiment and saw that only 2 of the balloons were blowing up, faster than the other 2 out of 4. The 2 that blew up the balloon was the one with the dry ice and water, which I predicted, and the bottle with the 7-Up in it, which I had to help by shaking it up a bit. After the experiment was done, I observed that bottle number 1 was slowly starting to blow up the balloon, much slower than bottle 2. The balloon on bottle 4 stayed small and never got any bigger. Conclusion. I had a fun time doing the science project and I learned how CO2 from dry ice can blow up balloons. Well, I was right about my hypothesis and how dry ice would blow up a balloon, but wet ice can't. Well, also, adding water and dry ice blew up the balloon a lot faster. I think the water and dry ice made the dry ice melt faster and gave out a lot more CO2 than the dry ice without water. This was a really fun experiment and I want to do this again.
Okay, so I had the volcano project. So my question was, will the volcano explode? When I was in kindergarten, I always wanted to do like a volcano project. Now that I can, I hope it works. So I think volcanoes are really interesting. I've done lots of research and informational papers on volcanoes. The volcano is not going to be like a real volcano, like a cone made of rock, but I think it's going to be pretty cool. And so my hypothesis was, if I had baking soda and vinegar together, what chemical reaction will I see? So if you want to do this, the materials are a foil tray, a jar of water that's 2/3 full, 4 to 5 tablespoons of baking soda, 1 teaspoon of dish soap, 5 to 6 drops of food coloring, which is optional, and 8 ounces or 1 cup of vinegar. So you put the jar in the foil tray, and you should do it on grass. Add 4 to 5 tablespoons of baking soda into the water, and then add 1 teaspoon of dish soap into the water. Then you put the 5 to 6 drops of food coloring into the water, then mix that together, and then add the 8 ounces of vinegar, and then watch for the reaction. And then, so while I was adding all the ingredients, the water changed to have different colors and mixtures in the water. It looked like a milk when I added the baking soda and Dawn soap, but once I added the food coloring, it kind of looked like red juice because I used red. And then while I was conducting the project, the vinegar made the whole thing explode. It was pretty crazy, and the red color foam looked like lava. And once it was done, it was kind of a mess, but the volcano experiment was really cool. So it was not exactly how I thought it would go, but either way, it's still actually really cool. So instead of shooting outwards like a real volcano, the foam just kind of ran down the sides, but I think it was actually really cool.
Hi, my name is Jacob Bakken, and for my science project, I'm going to do which fruit rods fastest, and my question for my science project is which fruit will grow mold first. My research and information for the last few years, my mom has kept a fruit bowl on our countertop, and it seemed to me that when I grab some fruit, the bananas are the ones that get brown first, and I end up not choosing to eat them. I read that fruits have water in them, so they can mold or rot faster than others. Bacteria and mold grow easier when they have water. I want to know if this is true, if that bananas rot faster than other fruits. Hypothesis. If the fruits in my bowl are packaged in the same way, in the same place, and the same time, then I think the bananas are going to rot first. The materials that I used. Fresh fruit, moist location, Ziploc bags for each fruit, big brown bag, and a dark location. Procedure. Pick fresh fruit dated about the same, cut them in half, put them in bags by themselves, put in moist location, check them once every 2 days for 10 days. Data and observation. Notes. Before, I need to get fresh fruit. They're about the same. I need to put them in bags and put them in most locations. I need to check them one time every 2 days. During. As you can see, the banana and the strawberries have the most mold and molding faster than the lime and apple. Lime because dark, kind of moldy. Apple is little moldy. Banana is really moldy. Strawberries is really moldy. After. As you can see, the banana is very liquidy and moldy, and so is the strawberry. The lime has turned yellow on the outside and the black on the inside. The apple is rusty, dry, and kind of moldy, but not as moldy as the rest. Conclusion. My hypothesis was if the fruits in my bowl are packaged in the same way, in the same place, and the same time, I think the bananas are going to rot first. I've done the experiment and the banana rotted first. In fact, it became the liquid.
Invisible Glass by me, Maylee. Question. How is glass affected by baby oil? Photos. When I filled the glass with baby oil, it disappeared, but when I rubbed it on the outside, it did not seem to turn visible. Rubbing it on the inside and outside did not make a difference. This is me pouring the baby oil into the container that was filled with baby oil. This is me sponging the outside of one container. You can't see the glass that I'm touching with my finger. It's pretty clear, but my finger is right on the edge of the glass on the inside of this bowl. It makes it pretty cool because it's completely invisible. This shows filled with baby oil, rubbed on the outside, rubbed on the inside, and rubbed on the inside and outside. There were 4 different containers that I did 4 different things with. Photos. This shows the 4 of them lined up. You can definitely see the difference between them. These look pretty similar because they aren't invisible, but this one, the inside, is completely invisible. I feel like some sort of mad scientist. And this is from the top view. You can see 2 glass circles, or bowls, I should say. One on the inside, one on the outside. And these are the other ones. They aren't filled with it, so there's no liquid inside of them. Hypothesis. Hypotheses. Hypothesis. 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 Glass will turn invisible when it is filled with baby oil. When baby oil is rubbed on the inside, outside, and inside and outside. Still 4 different containers. Materials. Baby oil. Glass bowls. Sponge. Procedure. Place a small bowl inside the large bowl. Fill both to the same height with baby oil. Get a sponge butt with baby oil. Rub it on the inside of one bowl, the outside of another bowl, and the inside and outside of one of the bowls. Data. Before. Filled with baby oil. The glass was visible all around. Rubbed on the outside. You could see the glass completely. Rubbed on the inside. The glass was visible. Rubbed on the inside and outside. You could see the glass. During. After they were both filled to the same height, the bottom went totally invisible. Rubbed on the outside. When I sponged baby oil onto the outside, it was still in sight. Rubbed on the inside. Rubbing baby oil on the inside did not change the outcome. Rubbed on the inside and outside. The glass was not invisible after I rubbed baby oil on the inside and outside. After. Filled with baby oil. The baby oil caused the glass to become invisible. Rubbed on the outside. The baby oil was of no effect. Rubbed on the inside. The glass was still visible throughout. Rubbed on the inside and outside. The oil must not have been strong enough, so it did not vanish from sight. Conclusion. Of my 4 tests, only the one in which I filled the glass with baby oil worked. This shows that baby oil must be gathered on the inside and outside of the glass bowl. Thank you for watching my presentation. Bye!
I wonder if it'll make the cat go away from the music if I change the volume.
research and information. When I researched, they said it may affect their behavior like humans, and this is what they said. The changes in physiology, and brain symmetry and morphology induces by music has been studied in animal models to provide evidence that music may affect animals. Similarity to humans, they conclude that the benefits of music to laboratory animals and depend on the species and the type of music. Alright, so hypothesis, loud music will stress the animal out and quiet music will not. Materials, phone, speaker, animal, camera, procedure. Add music, play music in front of animals, change music, take video. I couldn't really take the video because the cat was moving around and I was trying to control the volume and hold the speaker at the same time. Add and paste in my notes. And then we have here you go. And then on the notes, they were outside sitting on the chair and I started the music, but they were not scared because it was quiet. Then I turned it up a little louder and she started getting very scared and her fur got all spiky. Then she went around in a big circle and ran away. Alright, conclusion, my hypothesis is correct. It did affect the animal's behavior. I'm actually going to add a little more to that. And, yeah.
So my demonstration is blowing up Coke and Mentos. I've got a 28-ounce Coke and a pack of Mentos. I'm going to see how high this blows up.
You put the whole pack in, or just?
Yep.
How long is it going to take to blow up?
This is really quick.
Is it going to get on your computer?
No, it's too far away.
Why is it going to blow up?
I don't know. Well, I have my research in here. Forgot why though. Now ready for eruption.
You jump up all at once?
Yep. Now that was sad. That was really sad. That was sad.
Well, it had a reaction. That's all you needed, right?
Yeah. Let's see if we got any footage.
The materials are waxing paper, water, sugar, salt, gravel, sand, spoon, and some paper cups.
The procedure is in 1 cup, pour a spoonful of sand into a paper cup. Pour another spoonful of gravel into the same cup. Fill another cup with a teaspoon of water. Stir in 5 teaspoons of salt until it dissolves. Pour the salt water mixture slowly into the cup of sand and gravel until it is moist. Pour off any extra water. Let the rock dry. Then carefully tear off the paper cup over the piece of waxing paper. Let the rock set and harden for at least 2 days. In the other cup, do the same thing with sugar.